Thank you so much for joining this course. My name is Suman Devnath. I am a Principal Developer Advocate for AI and ML at AWS, and I am excited to have you in this course. In this course, we will start our learning by diving deep into embeddings, one of the most important concepts in the field of natural language processing and, of course, LLMs. We will explore few of the algorithms like Byte-Pair encoding or BPE and shall learn how to create embeddings using transformers and Hugging Face. Finally, we will also learn how to use few of the embedding models like Amazon Titan embeddings using Amazon Bedrock, which is a fully managed service for building generative AI applications with different foundational models at scale on AWS. After that, we will move on to multimodal models and shall learn how they are pre-trained, how they are used, and how you can use them with Amazon Bedrock. We will also learn about different models and architectures like contrastive language image pre-training or CLIP and bootstrap language image pre-training or BLIP. And finally, we will dive into the latest family of multimodal models from AWS called Amazon Nova. After that, we will shift our gears and learn about multimodal RAG or retrieval augmented generation. And we will build a system that can extract information from your data, which contains not only text, but also images and tables. And finally, in the last section of the course, we will build an end-to-end application to automate the insurance claim process workflow using agents and knowledge bases on Amazon Bedrock. I hope you will enjoy this course and have a great learning experience. And during this course, if you have any questions, feel free to ping me on LinkedIn or put a comment below. I will be very much happy to help you out. This is my LinkedIn ID, so please connect with me and share your learning. And before you get started, I would strongly recommend to clone this course GitHub repository and keep it handy for your reference as you go along with this course.
Just a quick note, Analytics Vidhya has 100 plus free courses from beginner to advanced on topics like machine learning, generative AI, agents, etc. Complete with certification. Click the I button to explore now.
In this section of the course, we are going to dive deep into embeddings for large language models. In general, embeddings for natural language processing. I thought that it might be interesting and important to explore how data is being treated by large language model. So we are not going to train a large language model or pre-train any model here, but we will try to understand how data is represented or pre-processed in the very first place before a language model is being trained. And this will give us a good foundation, or at least it will give us an intuition before we dive deep into different topics like multimodality with RAG and so on. So I have a notebook, as you can see here, and if you go to our GitHub repository, you will see a folder called Embeddings, and within that you will see this embedding for NLP notebook. Okay, so let's get started. So in this case, I'm referring a very good resource. There is a recently published book from Sebastian called Building LLM from Scratch, and I'm going to follow his notebook. I think it's chapter number 2 called Embeddings, and it's a phenomenal book. If you want to learn about LLMs and how LLMs are trained and fine-tuned, I would strongly recommend you to go over that book. So we are going to refer to a few of the examples that he shared in that book as a primary resource, and as we go along, I will share a few more very good resources which you can complement, which you can use to complement the learning apart from this course. Okay, so as you can see, we are importing a few libraries like TickToken and Torch. So this is PyTorch, and TickToken is a tokenizer. So for the moment, you can forget about this. We will come back to this little later, but we are going to use Torch. So let me import them and check their version. So as you can see, we have Torch 3.5, 2.5 and TikTok version 0.8. Okay, so this is the image which I took from that book from Sebastian, but we don't have to go over the entire pipeline. But what it is showing is, if you want to train a large language model, what are the stages and what are the processes? So the first process is to prepare the data, and then you have to build the attention mechanism, then the LLM architecture, and then you start pre-training your model, right? And then in the stage 2, we go over loading the data and fine-tuning and so on. So for this section of the course, we will spend time on preparing the data. So the idea here is we need to do a certain things before we send our data to any model, right? Because models, or any model for that matter, they don't understand raw text or raw audio or raw video. So we want to see how this data has been prepared and sampled. And for the context of this section, we will consider only text data, although the embedding philosophy, or the from a conceptual standpoint, it is very much similar, whether the data is of different modality. But for the sake of the discussion, for this section, we will consider text data. So as we discussed, we can have data of different types. It could be a video data, it could be a audio data, or it could be a plain text. So the idea here is we need to somehow represent this data in a way that a large language model can understand. And the way that we do it is using embeddings. What embedding essentially means is we take the data and represent it in an array of numbers. That's all it is. At its very core, all we have to do is we have to come up with a certain way or a certain methodology such that we can convert our data into an array of numbers. And that is what we are going to learn, what are these array of numbers and how we can generate them. So that's the whole idea of embeddings. So we will go over this example step by step, and we will see that how we can take a data and convert that into an array of numbers. So let's get started. So in general, there are different techniques historically we have where we converted our text into an array of numbers. There are different techniques like word-to-vec, glove, and so on. So if you take those into consideration and take a simple example, like let's say we represent our data into a two-dimensional space. What do I mean by that? Let's say you give us any data or any word, for example, and we represent that into an array of only two numbers. So one number is the one dimension, the second number is another dimension. You can think of it as you are representing every word in an XY coordinate. That's all. Right? So in that case, if you use traditional embedding models, which were available for quite some time before the LLM era, you will see that words which has similar meaning are very close to each other. So in this case, if you see eagle, duck, goose, they all are very similar to each other, and that's why they are very close in this 2D space. Whereas other places like Germany, Berlin, London, England, these are all name of city or country, so they are very close to each other. So that's the idea of embeddings, that we need to have similar words close to each other. But this is just for the sake of a simple example. But in real world, we do not represent our data into an array of just two numbers, but it would be an array of hundreds of numbers, or a very large dimensional space. So let's see how we can build this and what is the process behind it. So before we get into this, let's see why we need this and where we are in this whole journey of LLM from a training standpoint. So imagine that you are training a GPT like decoder or transformer. So if you have this transformer here, before you feed your data for pre-training or training, there are multiple steps that you need to do. Right? So let's say you have the input text as This is an example. So you cannot just feed this data directly to the model. So there are a sequence of steps that we need to go over. We have to first tokenize that. What do I mean by tokenization? We have to split the sentence in a certain way. Right? For the sake of simplicity, at this point in time, we can assume that we will break this sentence into words by just white spaces. So what we can do is we can just split this sentence with a white space as a splitter, and we will get different tokens. So these chunks or these single words, we can consider them as token. And then each of these token will be assigned a unique a number, and this unique number signifies what the token is in the entire vocabulary. Right. So if you assume that in the entire English dictionary we have 100,000 words, so this, if the token ID of this is 40,134, the way that you can think of it as, out of that 100,000 words, this has a token ID of 40,134, right? And then from this token ID, we have to generate an embeddings. Like every token ID will have a corresponding vector associated with that. Right? So we will go over this as we follow along. But for now, we are at this stage. So let's say we have a text. We have to first understand how we can break that sentence or a text into small tokens. So for this example, we have a book, a text file, which we have taken. So we have just downloaded this from a public repository. And what we are going to do here is we are just going to read that data and store that data into this variable called raw text. So let me execute this cell. So as you can see, this file contains a total of 20,479 characters. So it's not the words, but these are the total number of characters in that text file. And if you look at the first 99 characters, so this is the first sentence in that text file. Okay, so the goal of tokenizer is to break this entire chunk or of data, the entire data which we have stored in this variable raw text, into smaller chunks, right? So how we can do this? So before we get into this bigger file, let's take a small string or small text. So here we are using RE as the external library. So this is the library for regular expression in Python. So what we can do is, as we discussed a while back, that we can take a string and split it based on white spaces. So that's the easiest thing that we can do to split any text into tokens. So if we do that, you will see that we are getting different tokens like hello, then white space, then world, then again white space, and so on. Now, this is very trivial, but there are cases when we have a text and white space is not the only character to split our text. So we may like to split the data based on different splitters, right? Or different characters, special characters. So in this case, we are splitting not just based on white spaces, but different characters like comma, full stop, semicolon, and so on. So if we do that, let's see how our data would look like. So now our data looks pretty good. We have hello, then comma, then world, full stop, and so on. So these, you can think of it as different tokens, right? So this is a very simple way that we can tokenize our input data. So let's see how this mechanism of tokenization works for our entire data set that we have. So since we tested with only our small text like one line, now we are going to use the same but on the entire file, the raw text, which was the variable we have created, which contains the entire text file, right? So we are going to do the same thing here, and let's see how the processed tokens looks like. So if you see here, we have processed the entire text, and we can see the first 30 tokens in this particular text file. Right. So if you see that how many tokens we have, we can simply use len function to find out the exact number of tokens in that entire file, and that happens to be 4649. So we were able to tokenize the data that we had. Now, of course, these number of tokens are not unique, right? Because if you see here, in the first 30 tokens, we saw A here, and we again saw A here. So this is, we have duplicate tokens, so we can certainly find out a unique set of tokens of this processed file, but we somehow able to tokenize our data. Now we will see whether this tokenization technique is good or bad, but we were able to achieve the first objective, where given a text, we should be able to tokenize the data. Okay, so at this point, if you give any text, I should be able to give you a tokenized version of that. Now the second step in the process is to give a unique number to each tokens. Right? So if you remember, if I scroll up, if you remember here, when we discussed this has a token ID of 40,134. Is has a token ID of 2052. So this is just a random example, but this is what we need to achieve. We were able to achieve till this much, right? So given a text, we were able to tokenize that. The next step is to find out the token ID. So let's see how we can do this. So this is our processed tokens, right? And as we explained a while back, that this process token contains duplicate tokens. Right? So because in a text file, you will have a same word appearing in multiple times in different sentences or within the same sentence. So if we use set, we will get a unique set of tokens. And what we are doing here is we are just sorting it in an ascending order. And now if you see the total vocabulary size, it's 1159. So imagine that this is the vocabulary of English language. Just for the sake of simplicity, just imagine that we have scanned through all the data on this internet, and we tokenized it using white spaces and some special characters, and we found out that these are the unique number of tokens, right? So now the next step would be to give or assign a unique number to each token, and that we can simply do by looping over the entire list and give them a number starting from 0. So that is what we are doing in this dictionary comprehension. So we are just enumerating over all the words, and we are providing an integer to every unique tokens. So now if you see the first 50 tokens, you will see something like that, right? So this exclamation mark, it has a token ID of 0, A has a token ID of 11, and so on and so forth, right? So this is how we were able to tokenize the data and also assign a token ID to our data, or to every token. So at this point, if we have a text or a string, we should be able to break that sentence into tokens, and then we can actually assign token ID to each of these tokens, right? So from this sentence, we can easily come to this array of token IDs. So let's try to build a simple tokenizer with this technique, right? So what we have established. So now what we are going to do is we are going to wrap up everything that we have tested so far into a simple class called simple tokenizer version 1. Okay, so we named it as version 1 because we will be building on top of it and make it better. So this class contains two methods. One is encode, another is decode. And as the name suggests, encode will encode the text that you provide, and it will process it by simply doing some pre-processing. As we have seen earlier, it will just split based on some special characters. And once that is done, it will just return the IDs of each token given the vocabulary, which we have already created by reading that text file. Right? So imagine that the text file contains all the words that we have in English dictionary for the sake of it. But in real world scenario, this vocabulary will be huge. Right? In this case, it's very small because we have used one text file, but in real world, it would be huge. So encode will, this method or function encode will encode your text into token IDs, and decode will do exactly the opposite. Given the token ID, it will generate, or it will have a lookup with the exact tokens. Okay, so let's create this class. And now if we provide a string like this, it should be able to give us the token IDs. That is the encode method. And similarly, when we call the decode method, and if we pass this token IDs, it should be able to give us the text back again. So let us test this and see how this works. So first we have to call this tokenizer, or create an instance of that, and we need to pass the vocabulary. So this is the vocabulary which contains all the words that we have in our corpus. So once we create this tokenizer, we can send any text. So let's say this is the sample text that we have, and we call the encode function or encode method. And let's see what are the token IDs we get. So as you can see, these are the token IDs of different tokens in this text. So far, so good. So now let's try to decode that. So if we pass these IDs to the decoder or decode function, we should be able to get the tokens back. So let us see what we get. And sure enough, we are getting the same text back. Right? So this is working pretty fine for us as of now. Right? So we are able to tokenize our text to an array of numbers, which are the token IDs, and we are able to get back to the tokens given those IDs. But now let's try to send another text. So let's say I'm just uncommenting it, and I don't have to create the tokenizer again. So let me comment this, and now let's say we have this text. Okay, hello, do you like tea? So this is just a sample text, and let's try to encode this text using our tokenizer. And it seems that it is not working, and we got an error called key error, and it seems that hello is not there in the vocabulary. So what might have happened is the text file which we have used to process or to create our vocabulary, that text file doesn't contain the word hello. And we can in fact see that we have this text file. So this is the text file which we read to create the vocabulary. If we search for hello, you will see that there is no result. So this seems to be a problem, right? And this seems to be a problem because in real world, this is very common. Because imagine that you have started off with a certain corpus by knowing all the words that you know at in today's time, and you trained a model. And later on, when the model got trained after a few months and a few weeks or a few months, when you put that model in production, and when you send a text for inference or give a prompt, it might so happen that you give a word which was recently added in the dictionary, or let's say it's a new word which was never encountered by the LLM at the time of training. So in that case, we will get these kind of error, which is certainly not good. So let's see how we can modify our tokenizer such that it can handle these kind of out of vocabulary situation. Right? So one of the very intuitive or very logical thing to do is to have a token, special token called let's say unknown token, and have it in our vocabulary. In that case, what will happen is whenever we send any token which we don't have in the vocabulary, it will have that token as a that special token as a default token assigned to that, right? Which may not sound that great, but it at least will take us to a place where we will not get these kind of key error, right, or out of vocabulary error. So what we can do is we can add some special tokens, like here if we add a special token called unknown, and let's say another special token called end of text. So end of text a lot of times are used in LM while pre-processing the text, where we need to add this to make a distinction that the data that we have is coming from a different file, because in real world we will have a large corpus of data, and all this data will be coming from multiple files. So if we tokenize all the files together, we would not know when the first file is starting and when the second file is starting, and so on. So if we have a tokenizer, a special token called end of text, we can somehow use that in front of every new file. So if you look at this image, so let's say these are the different files that we have, and this is the first file, and this is the second file, this is the third file, this is the fourth file, and so on. So if we add a special token called end of text and send all these files together, after encoding we will have a way to identify from where the second file is getting started, because we have added a special token here. So which type of, or what are the different special tokens you want to add, it's completely up to you. There are different types of special tokens which different models uses, but for the sake of simplicity and for this example, let's add two tokens. One is end of the text special token, and the other would be the unknown token, so that if any word which we encounter in future which is not in the vocabulary, we can assign that unknown token to that. Okay, so if we recall, our length of the total vocabulary is 1159. So if we add the two new tokens, like end of text and unknown token, we should get the total number of vocabulary should increase by 2, right? So let's try to do that. So we already have this much we have already seen. So we already have all the tokens from our pre-processed data. Now what we are doing is we are just extending it with two new tokens. And since we have extended into with two new tokens, we have to assign a token ID as well for them. So we are just doing the same thing what we have done before. We are just enumerating over all the tokens, and we are assigning an integer for that, right? So let's run this, and now if we see the total number of tokens, it is now 1161, right? Previously it was 1159, so we just added two special tokens. Okay, so now if we just look at the last 5 tokens, you will see that these 2 tokens got added. So it's pretty natural, and this is very much expected. So with this, we should not get an unknown token, right? So if we encounter any unknown word which was not present in our initial vocabulary, we should not get this error which we got previously. So let's update our simple tokenizer, and that's why we are calling it as version 2 now. And the entire code is exactly the same. It's just that we added a new vocabulary. And one of the things that we have to do is we are adding a special step here which just checks whether a certain token actually exist in our vocabulary or not. If it exists, we will just keep it as it is. If the item is not there in our vocabulary, then we will assign this unknown token. Right? That is the logic that we discussed so far. Right? So this is the only change we have in this version 2 with respect to version 1. So let's create this class. And once we have this, now let's try with the same text. So let's say we have a text called hello, or do you like tea? And then we have another text called in this sunlit traces of the place. So this is just a random string. And if we just join these two strings, we will use a special token. As we discussed, imagine that this text 1 is coming from file number 1, this text 2 is coming from file number 2, and when we pass this, we will add a special token between these two, so that we understand that when the first file is getting over and when the second file is getting started. Right? So this is just an easy way to differentiate the start and end of any text. So this is our text, and now if we encode this, we should not get any error while tokenizing. And rightly so, we are not getting any error, and we are able to get the token IDs. Right? And if we decode it back, so if we just, this is for encoding, if we just decode it back by running this decode method, just calling this method, we should be able to get the string back. And in this case, you can see that we got a different text, not the same text which we added, and which is quite obvious because we have replaced hello with unknown. Right? That is something is very much expected. And we also got a special token called end of the text, and the last token got also replaced by unknown. And let's see what was the last token. So the last token was actually palace. So if we just search for this palace in our vocabulary, I'm very sure it should not be there. So let's try for palace, and sure enough, we are not able to see that token in our initial vocabulary. Right? So with this, we can conclude that we are able to tokenize our text data using some special tokens that we added. Right? But this is not something which is great, because in this case, if you see here, when we decoded, we got the same token for two different types of words, or two different words. One is hello and one is palace. Right? So this is not good. So this technique is not very efficient because if you have a text which contains lot of tokens which were not there in the initial vocabulary, we will not do justice in identifying all these tokens. And furthermore, in the downstream process, the LLM won't be able to generate the right response, because it is going to generalize the text in a one dimensional way, that everything is unknown, right? So that is not a good way to tokenize our data. So this is where we need to think about how we tokenize the data. Now we will learn about one of those very famous technique called Byte-Pair encoding. So this is a tokenizing or encoding algorithm or method which many of the large language models that we know today has been using, and it is very popular. It has been implemented in GPT-2. So the tokenizer that we use in GPT-2 is based on Byte-Pair encoding. So now let's see how Byte-Pair encoding can help us in all this out of vocabulary token scenario. Right? So I have a beautiful presentation from Professor Mitesh from IIT Madras. So let me just open the presentation, and so that it has a very beautiful visualization. So I think that would be very easy for you to understand. So I have added this link into this Jupyter notebook. So at a later point in time, I would strongly recommend you to go over that to understand even more about this. So let's open this. I guess I have opened this in a different tab. So let me expand and show it to you. Okay, so imagine that, just to revisit where we are, we want to achieve and build a tokenizer such that it can surface our requirement of unknown vocabulary, and also it should be efficient, right? So one of the simple technique that you can think of while thinking about tokenization is we can tokenize the text at a character level, right? So if you give a word, you can always break that into single characters, and that could be your vocabulary. Or in the other extreme, you can have all the words that are available on this planet, and you can create another vocabulary. So both of them has limitations. First is, if you use a character level vocabulary, then your vocabulary size will be small. Like, let's say if you consider A to Z, there are 26 characters, then A to Z in capital letter, maybe 26 more character, and then there are some special characters. So you can think of it like you can have a entire vocabulary of size maybe 200 or 300. Now, if you do that, then when you give a text like, let's say, my name is Suman. If you give this text, then my entire the embeddings of that would be very, very large, because now every word, like my name is Suman. So Suman is contains 5 characters. So each character will get a unique token, or will be treated as a unique token, and each of those token will be later on converted into an array of numbers. So it will be very cumbersome to perform the embeddings on even on a smaller text. So doing the embedding at a character level may not be a very good idea. So let's say on the other extreme. On the other extreme, we can have all the words on this internet. So in that case, we will have millions of words. So that is also not very good, because at the end of the day, if you think about any large language model, it's a probabilistic mechanism where it just generates one token at a time. And that one token is selected from the available vocabulary. So if I have a vocabulary of millions of words, and every time I have to pick one word from that millions of words, that is not very efficient. So the problem is this: we need to find a technique such that we can stay somewhere in the middle, not completely word wise, where every word is a token, and not at a character wise, where every character is a token. We have to come up somewhere in the middle, right? So that is where a subword, a tokenizer is all about, and that is what Byte-Pair encoding is. So let's take an example. So let's say this is a sentence. Knowing the name of something is different from knowing something. Knowing something about everything isn't bad. So imagine that this is our entire corpus, right? So this is our entire vocabulary. Now we will spend some time to understand how Byte-Pair encoding works. So the first step in Byte-Pair encoding is we do some pre-processing and we split every word, or we just split the sentence into every single word by just, let's say, white spaces, and we add this special character /W. So this is just to identify the end of the word, right? So this is just an identifier for word boundary. So our objective is to find the most frequently occurring byte pairs, right? And we will get into that. What do we mean by this? But the first step is We take this text and we split it based on white spaces, and we add this special character called /w as a word boundary, right? And imagine that this is the entire corpus that we have in our dictionary, right? So that is the initial data that to get started. In real world, this would be huge, right? This would be like this, millions of text file that we might process. Okay, so the first thing that we will do is we will count the frequency of each word in this entire corpus of data. So in this case, the word knowing has occurred 3 times, and that's why the frequency is 3. The word the occurred 1 time, so that's why the frequency is 1. So that is the first thing that we will do. Okay. So now that we have this frequency count of each word, the next thing that we need to do is we need to count each character, right, and update this table. So this is going to be our initial token count. So we will start with the character K because let's say the first word is knowing. So we will just start with the first character K, and we will see how many times K has occurred in this entire corpus of data. So K has occurred only in this word knowing, and since the knowing has occurred 3 times, so the frequency count of K is just 3. So like this, we will have the frequency count of all the characters, right? So let's try with the next character. The next character is N, and N has occurred 13 times, right? So if you want to know how that 13 have come, we can find out that N has occurred 2 times in the first word. So that's why this is N 2 times 3, it is 6. And if we find more, we can go to the next token, and the next word is name, and here also we have N. So it is 1 times 1, that is 1, and so on. So if we keep on finding N in our corpus of word, we will see that the total number of times N has occurred is 13. Okay, so like this, we will keep on doing for all the characters, and this will be my initial token count, right? So this is what we are going to get started off with. So this is very much like a character-based tokenizer, and that is our initial starting point, right? So if we recall, we mentioned that character-wise tokenization is not that good because it is limited, and word-wise tokenization is not good because that's a huge corpus. So we have to come somewhere in the middle. So what we are going to do next is we start off with character-based tokenization, right? And we will keep on merging the more frequent pairs of characters, and then we will keep on merging them, right? So what do I mean by that? So this is my initial corpus or initial token counts. The next thing that we are going to do is we are going to merge 2 tokens at a time, right? So for example, in this case, this is our initial vocabulary size, which contains 22 tokens. That means 22 unique characters in this whole vocabulary. Now we have to start from here. So my the end vocabulary will be somewhere more than 22, and we can decide when we should stop. Okay, so let's go to our second step. So this is where byte-pair counting comes into picture. So now we will take 2 characters at a time and we will count its frequency. So in this case, our first pair, byte pair, is K and N, and since it has occurred only in one of the word, and this word has occurred 3 times, so the frequency count is 3. Similarly, NO, the frequency count is also 3, and so on and so forth. So we will keep on doing this for all the byte pairs. And once that is done, we will try to find out which pair has the maximum number. So if you see here, the maximum count is IN and NG. Both are 7. So in case of any tie, so in byte pair, what we do is we just take the first one. That's a random choice, but we just take the first one. So now this pair will be added into my initial vocabulary. So my initial vocabulary was having only the unique characters. Now we are going to add IN into this initial vocabulary. And intuitively it makes sense as well. It means that IN occurred the most amount of time, right? So that means that whenever I occurred, N also occurred. So that's the intuition, right? Why we are even considering IN, because we are seeing that IN occurrence of IN is very high, right? That makes sense as well. But when we add IN, we have to adjust the vocabulary count of N and I, because 7 occurrence out of this 13 has been already counted here, right? So we need to update the count here as well as for I, because here we are saying the total number of times I has occurred is 10 and the total number of times IN has occurred 7. So this should be also updated, right? So that is what the next step is. We need to update the count of the existing tokens based on the present newly added token, okay, which is in this case. So once we have this, after the first merge operation, this is where our vocabulary would look like, okay, and like this we will keep on doing the merge operation. So every merge operation will add a new byte pair into our vocabulary, and that is how this byte pair encoding works. So similarly, next time, once we add this, next time we will have different byte pairs, right? So if you see here, we have IN as a byte pair now. Now what we are going to do is we are going to have different pairs. So now we will have ING as well. So IN is already there in our vocabulary. So we will now try to merge IN and G, right? Similarly, other tokens as well, but this is just for the sake of example. And we realize that ING has occurred the maximum number of times, and similarly we will add ING as well into our vocabulary. And when we do that, we have to again update the count of the existing tokens based on the newly updated token. So that's the whole idea of byte pair encoding, wherein you start off with initial set of characters of your entire vocabulary. After you do some pre-processing, you will find out the initial set of characters based on the frequency, and then you keep on adding or merging 2 characters at a time, or merge the tokens one by one, and keep on taking the byte pair which has the maximum frequency count. So if you do a lot of merges, at the end you will find your final vocabulary. So in this case, if we add, let's say after 45 merges, we should be adding 45 new tokens. So the total number of tokens that we will have for our vocabulary is 45 plus the number of initial tokens. So let's say the initial number of tokens is 20. So the total number of tokens would be 65. So that's how this whole byte pair encoding works. Okay. Just to summarize, if you start off with an initial number of tokens, which would be a character-based tokenization. So let's say that is 100, and then you do 200 merge operation. So in that case, your total vocabulary size will be 200 plus 100, that is 300. Okay, so that's about byte-pair encoding. I just thought to give you some intuition about that. You can go over this presentation. It's a beautiful presentation to learn more about this, but I think this is enough for us to get an intuitive understanding of what byte-pair encoding is. So what we are going to do is we are not going to implement a byte-pair encoding, because that would need a large corpus of data. But what we are going to do is we are going to use the byte-pair encoding tokenizer which GPT-2 has used. And for that, we can simply import this tick token module or the library, and we can use, or we can extract the GPT-2 encoder, and this will give us the tokenizer which we can use for our work. Okay, so let me import that and just check the version, and we can get the tokenizer. So this is the tokenizer which GPT-2 has used, right? So this particular tokenizer has a lot of tokens. So let's see how many number of tokens that they have. So they have 50,257 tokens. So this is very much similar to the tokenizer which we have created earlier with our corpus of data, which was just a text file. But now we are just loading it from a tick token, right? So this tokenizer should be able to handle unknown tokens, and also it has a richer understanding of data, because this has been trained on a large corpus of data, right? So if you want to test it, you don't have to go with GPT-2 tokenizer. You can always go with any other tokenizer. And to find out different tokenizers, you can use this list encoding names method, and you will see that there are different tokenizers which are available, right? And if you want to see what is the vocabulary size of different tokenizer, you can just use this nvocab variable. You can just call this and just read the value of this parameter nvocal, and you will see that different tokenizers will have a different vocabulary size, because they were trained in with a different set of data, initial corpus of data, and so on. And going forward, when you look at different tokenizers, you will see that the number of tokenizers or number of tokens are increasing, right? With the latest and greatest models. It's a very common and natural thing to observe. Okay, so now let's try to do something interesting, right? So now let's say we have some text, right? So you can pick any text of your choice, and then let's try to encode this text. Just like before, where we have implemented our own tokenizer and send our text, we used to get an array of numbers which are nothing but token IDs. In this case, we are doing exactly the same, but we are using a GPT-2 tokenizer. So there is nothing special about it. So if you see, here are the array of numbers that we get, which are nothing but the token ID of all the tokens which the this particular GPT-2 tokenizer has observed. Now, if you carefully see, there are some words which makes no sense. So, and we deliberately using this. So there is a word called some unknown word. So this we kept it as a single word which has no meaning. This is not a dictionary word. So in our technique, this should have been replaced by unknown token, right? Now let's see how this byte-pair encoding has tackled this unknown word or this out of vocabulary word. So if we now decode this and check the string, and you will see that we are getting the exact same string. So it was able to chunk or tokenize this word, some unknown word, right? And this is the beauty of byte-pair encoding. And the reason that it could able to decode this is because we used byte-pair encoding. So what might have happened is, in the vocabulary, this this token, this particular word, some unknown word token might have been divided into some, unknown, and word, because these are very common words, right? So depending on the vocabulary that this GPT-2 tokenizer have, it was able to decode that. So this is the usefulness of Byte-Pair encoding, where it can handle unknown tokens or unknown words at the runtime, right? So that is the reason why Byte-Pair encoding works pretty well in large language model, and one of the major reason is it can handle unknown word which was not present in the vocabulary, and the reason that it could able to handle is because of sub-word tokenization. So it actually tokenized the word at a sub-word level. So if you remember, when we started off this section, we assumed that every token is a word, but in real world that is not the case. And if you look here, this particular sentence, right? So this particular sentence contains how many words? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 words. But if you see the number of tokens that it has generated, it's not 12, it's much more than that. In fact, we can see this as well. So let's try to see the length of this. It's 21. So 11 words got converted into 21 tokens. So from now onwards, if somebody says that every token is a word, which is okay for explanation sake, but in real world or at its core, that is not how tokenization works. Okay. So now that we know that it can handle unknown words, we can always throw any garbage word or any word which is not there in the dictionary. And like in this case, we are just passing this unknown word. This is not a regular dictionary word, and it should be able to decode that, right? And if we take this same array of numbers and if we paste it here to decode, we will be getting the word back as it is, right? So this is one technique to tokenize our data, right? So we are able to come to a stage where we, given a text, we will be able to convert that into token IDs. Now, the second thing that we need to do is when we think of training an LLM using a large corpus of data, is called data sampling. So the way that any LLM is trained is a self-supervised way. So what do we mean by that? Assume that you have all the data, all the corpus of data, Wikipedia data and all of that. And let's, for the sake of simplicity, let's consider only text, as we have been doing since the beginning. If we have the entire text of data, what we want the large language model to do is, at the end of the day, is it should be able to predict the next token, or it should be able to generate the right token one after another, right? So when you go to ChatGPT or any LLM or any application based on LLM, when you ask a question, you get a response, and that response that you get, it generates one token at a time. So it just generates one word or subword at a time. So when we have our training data, like the entire Wikipedia data, what we can do is, since we have the entire data, we can send only the first token, and we expect the second token as the response, right? So we know that the second token here is learn. So if I give LLM as the first token, we expect the model to generate learn. Similarly, when we give this phrase LLMs learn, we expect the token 2 as the prediction. So basically, I'm just sliding by 1, and we are able to generate the samples of x and y. So when the given the input is x, which is these 3 tokens, we expect the output as predict. So just by it's a self-supervised. The reason that we say it as self-supervised is because in normal supervised machine learning, we always need to give the x label and the y label. But in this case, we are just having the data. So that you can consider as x, but there is no y label. But from that x itself, we can develop y, right? So, and that is how we are developing, because we have the whole corpus of data. We can just slide by one token and we expect the model to generate the next token that we have, right? So let's see how we can do this. So just like before, we are just reading the text file, and that is going to be our entire vocabulary, and we are going to use the tokenizer that we have created using GPT-2. Okay. So the length of the entire corpus of data is 5145, right? So this is the total number of tokens that we have in our training set, right? So now the first thing that we have to do is we can before we go ahead, we have actually gone through the text file, and we felt that the first 50 tokens we can skip because it has some introduction, name and all that. So just for the sake of this example, we are just getting rid of the first 50 tokens, right? So if you want to use any other file of your choice, you can very well do that. In that case, you can just skip this part. Even if you don't do this, that is also okay. But since I've read through this file, I realized that the first 50 tokens are of not that use, right? Roughly around 50 tokens. Okay. So the way that we will generate our x and y for us self-supervised training is by this. So let's say my context size is 4. Okay. So the way that I will generate the samples as like this. So we can start from the very beginning and take the first 4 tokens, and then the y would be starting from 1 to the token plus 1. So let me print this so that you get a better understanding. So my tokens are this, right? So this is my encoded text, and this is the sample, right? So this is the entire vocabulary that I have, or the entire text that we have. Now, when the first token, so this is an x and y, and see this very carefully. I have used the same data to construct x and y. So in regular supervised learning, what we do is we give something like x and we have some y, right? So this is how we always get the training sample. But in self-supervised, what we have is just we have x, right? So we don't have a y. So what we will do is from this x, we have to somehow find out x and y, right? So this is the technique that we are trying to implement, right? So in this case, the x contains the entire corpus of data. Right? Now we have to somehow find out y, because we know the nature of this problem, which is just a next token prediction. That is what all the large language model do. So we can somehow establish that fact. So let me delete this and show it to you how this works. So the first token, if the first token is 290, I expect the LLM to generate this token 4920, right? So similarly, if the input is first 2 tokens, then I expect this third as this 2241 as the y as the generated token. So let me print out the actual tokens so that you can get a better context. I had the sentence this, right, and established himself in, right? That was the exact sentence. And the way that we have segregated that X and Y pair is like this. When the input is AND, the response should be established. When the input is AND established, the output should be himself, and so on. This we were able to generate just based on this one sentence, right? And that is why we call this technique as a sliding window technique, right? So if I just scroll back, if you just see, we just had one line here, right? LLM learned to predict one word at a time. This is just one line. So this is the only text that we have. Now from this text, we were able to generate 1, 2, 3, 4, 5, 6, 7, 8. 8 pairs of training samples. Right? And how we were able to do that? We were able to do that using a sliding window technique, where we start from the very extreme left and we process it in such a way that when the X is first token, the expected token should be learn. When the input is the first 2 tokens, the output should be the third token. When the input is the first 3 tokens, the output should be the fourth token, and so on. Right? So this is how we can construct our data set to train our LLM. Right? So this is called a self-supervised technique. And here in this case, we just took a context size of 4, but in real world it could be something else, and we will see that in some time. Okay, so now that we have done this, we can now implement this using a data loader, right? So that we can use this data for any LLM training or any model training, right? So we are going to use PyTorch for this. So I've just imported PyTorch. And now what we are going to do is we are going to use the PyTorch data set and data loader class to create our data set and the data loader, right? So just because the code is very simple, but understanding of this code is more important. So if we have a text like this, we will slide by 1, right? So if you see this, the blue box here, if the input tensor is in the heart of, right? If this is the input, then the output tensor for this, so that means the labels or the target would be just the tokens with a slide of 1. So it would be the red box, right? So the heart of the, right? So this is where you see that the heart of the, right? So when the input is in, the output should be the. When the input is in the output should be heart, and so on and so forth. Right? So that's the basic intuition of sliding window. Right? So here we are just creating a data set, and this is our own custom data set. And in this 3 lines of code, we are exactly doing what we have just explained, just to implement the sliding window technique to just go over the entire corpus of data. Right? So let's create this data set, and then we will have a data loader which will load the data. Right? And in this case, we have to mention what type of tokenizer we are going to use. So we are going to use the Byte-Pair encoding based tokenizer, which is GPT-2 tokenizer, which we have seen earlier. And then we will just take a batch of 4. So this is the default, and whatever is the maximum length. In the previous example, I think we saw the maximum length as 4, but you can put whatever number that you would like to. Right? So this will give us a data loader. So now with this, we can load this data and start the LLM training. Right? So that's where we are getting into. So let's now read our whole file. So now that we have our test data loader and data set created, or the class created, now we can create a data loader. So we will load the whole corpus of data, which is this text file that we have been working on from the beginning, and we create a data loader. Right? So we will just give this raw text. We here, for the sake of this example, let's start off with batch size as 1 and maximum length as 4 and stride of 1, and then we will just load the first batch, right? So first batch should contain 4 tokens because the maximum length is 4. So let's see this. We got the first 4 tokens, right? And this is the X and this is the Y, right? So just exactly same as what we have seen earlier, right? When the input is this, the output is this. The data loader, whenever we load the data and whenever we call the data loader, it will give the X and Y, right? That's how a data loader class works in PyTorch. If you want to see the next batch, we can call, this is an iterator, so we can just call this next function. And if we print the next batch, you will see the next batch, since the sliding window is 1, it should start from 367, and that's what you see here. The first is 367 on 28285 and so on. And so this is X and this is Y. Okay, so that is how we were able to iterate and tokenize our data and iterate through this. So now let's take a more concrete example. So in this case, now we are creating a batch size of 8 and the maximum length is 4, right? So that means every time we load, we will get an XY pair of 8 such samples, right? So let's see this. So in this case, I'm just calling the same next here, but now we are not getting just one tensor, we are getting 8 tensors. And the reason that we are getting 8 is because the batch size is 8. Okay? And since the maximum length is 4, we are just getting 4 tokens. Okay, so when the input is this, the output should be this. When the input is this, the output should be this. Right? So that's the whole idea of this. Okay, so till now we have been able to take the text, process that text, convert it into tokens or chunks. Not chunks, chunks may not be the right word, but tokens. And then we assign a token ID. And this numbers are coming from the GPT-2 tokenizer, but you can use any tokenizer of your choice and you will get these numbers. Now the final thing is not these numbers, but each of these numbers should represent a unique vector. Right? So that is the whole idea, that every token should be converted into an array of numbers. That is what we are going to do now. Before we see that how we can get those array of numbers, let's take a simple example. Let's say we have these tokens and the token IDs are 2351, right? Just for the sake of this example. So let's assume that our total vocabulary size is only 6. Okay, so total number of, let me just write it here. The total number of tokens is 6. Okay, so that means it will range from 0 to 5. And after tokenizing of our input data, these are the token IDs. Just like before, if you remember, these are the token IDs that we got from our input data when using GPT-2 tokenizer. In this case, just assume that we have done some pre-processing and these are the tokens, token IDs of the text. Now, in that case, how we will convert these tokens into an array of numbers. So if the vocabulary size is 6, which we have considered here, and now we can define the length of our embedding vectors. That means here in this visual example, you can see that we are trying to represent each token into an array of 3 numbers. So in real world, this length could be very high, like 100, 200, 300, even 400 or 1000. And the bigger it is better, because you are able to represent your data in a much higher dimensional space, and every dimension has some unique information about that token. So in this case, let's say our vocabulary size is 6, that is given. We can change this number. So let's say we want to create an embedding model where the length of embedding is 3. We can mention that as 3, and we can create an array of 3 numbers by using the torch NN module, and we can use the embedding layer, and we can give the vocabulary size and the output dimension, right? And we will get a 6 by 3 matrix, right? So this is the matrix, what it would look like, and these are just randomly initialized numbers. But what this intuitively means is that the first token's embedding is this, the second token's embedding is this, and so on and so forth. So since our total vocabulary is just 6, that means there are 6 unique tokens. So we need to have 6 vectors representing these tokens. And the way that I can create 6 unique vectors is using torch_nn.embedding. Okay. Now these are not trained, these are just randomly initialized. What happens is during the LLM training, during the backpropagation, this embeddings are also learned. So at the end of the training loop, or after we optimize and we get to a point where we feel that this is a good model, we just stop, and then we get a frozen set of numbers which we consider as the embeddings of different tokens, right? But this is how it all gets started. So you start off with an random initialization. So there are different techniques to initialize, but this is not the final array of numbers. Okay, and you can think of this as these 3 numbers representing 3 different things about every token. Right? So for example, the intuitive meaning of this is, let's say you know me, and you just know 2 things about me. One is my name is Suman, and the second thing you know is that I work for Amazon. You just represent me into these 2 things, right? So you can think of it as you are representing me in 2-dimensional space. Now, if somebody asked you, can Suman play cricket? Now you cannot answer this based on just these 2 information. But imagine that I have given you 5 different types of information about me. So let's say if I say, my name is Suman, I work for Amazon, I used to play cricket in school, I used to play basketball as well, which is not true. But if I give you more information, what it essentially means is you are representing me in a higher dimensional space. And now the probability for answering any question about me correctly is much higher. So if I use a higher dimensional vocabulary size here, so let's say if I use 10, right? And if I use this now, I will see, oh, sorry, not the vocabulary size. So vocabulary size is 6, but let's say the output dimension is 10. Now, every token in my vocabulary is represented into an array of 10 numbers. So previously it was 3, but now I have added more information. So that is the reason when somebody says, if the embedding length is higher, is it better? Of course it is better, provided that the added information is unique. For example, if I tell you a few things about me, but not just my name and company, but if I give you more information, something like my name is Suman, I work for Amazon, I play cricket in the morning, I play cricket in the evening, I used to play cricket in the school, I used to play cricket during my college. So I have given a lot of information, but if you noticed, last 4 or 5 set of information are quite redundant, right? So that is not adding new value to you. So that's why we say that when the embedding length is bigger, it is always good, assuming that it has been trained properly, and we know that these columns are linearly independent, or rather they all contains unique information. In this example, we have just considered an array of 3 numbers, and these are the random initialization, and during the training process this weights gets updated such that every token will end up having a good information which are semantically similar. That means an embedding of cat and embedding of, let's say, dog may be little similar, because they both are animal, and they both have 4 legs, they both have tail. So the embedding of these two are expected to be very similar, and we don't have to do this of our own, and we cannot do it of our own as well, but these are learned during the training process. Okay, so now if we just let's say this is our embedding metrics, and assume, for the sake of simplicity, let's assume these are the trained weight. Okay, so these are not the trained weight, as you have seen that we have just randomly initialized, but assume that this is our trained weight. After the training and all that, this is the final embedding metrics that we got. Now if we have a token of ID 3, I can simply run this, and I will find the 4th row from here, right? So this is my 4th row, and it is just a lookup. It will just look into the embedding metrics, and it will just find out the embedding which is there in the 3rd token. So 3rd token is nothing but the 4th row, because it's indexed from 0, and this will be the array of numbers which represents the token number 3. Okay, so similarly, if I have to do it for okay, I'm sorry, I think token IDs. Okay, I think I have not executed this, but this is the token IDs, right? So let's say these are the token IDs, input token, and now if I pass this, so let me just copy this and keep it here. So let me copy this, and let's say these are the tokens that I have, and if I want to generate the embeddings of this, it will just refer to that embedding matrix, and it will find the vector for ID number 2, 3, 5, and 1. Right? So it's basically a lookup. So if you see this, the token number 2 is nothing but the 3rd row, and the 3rd row starts with 1.27, and that is what we are getting here. Similarly, the 5th one is this minus 2.84, and the 5th one would be the last one, and that is exactly the same vector. Right? So that's basically a lookup table. Now this is all good, but there is a problem in this, and the problem is we are not considering the positional information of any token. So if you look carefully, we have created the token IDs, and every token ID has a corresponding array of numbers or a vector. But if we have the same token appearing in a sentence in a different position, there is no way that we are capturing that information. For example, here, if you see this, let's say this is our embedding metrics. So these are like, consider that our entire vocabulary is just contains 6 tokens. So in this case, if I have a sentence like this, where fox is coming in the first token in the sentence, in that case, the embedding of fox would be this, right? The second index in the weight matrix, and assume that we have another sentence where fox is also there in the last token, or the last word in the sentence. So this is the same sentence, but fox is there in the first, fox is also there in the last. So in this case, the embedding of this vector and the embedding of this vector is the same, which is not good, right? Because these embeddings should contain the information of its position. Because we often know that when we speak in any language, for that matter, not just for English, when we speak, where we place a certain word has a bigger impact in the meaning of that entire word, because it very much depends on the context that we are talking about. Right? So this is the last step that we are heading towards, where we need to come up with a strategy where we can embed the positional information of the token as well when we do the embeddings. Okay, so there are different techniques of embeddings, and one of those techniques is called absolute positional embeddings, where we assigned an absolute value for a certain position of every token, and we just add that with our input our embeddings, right? So let's say this is our token embeddings, right? So just for the sake of simplicity, it's all one. Assume that the same word coming multiple times, and what we do is we just add a positional embedding. So that is another vector of same size. It should be of exactly same size of the token embedding, but we just add this. And if you noticed here, we are adding a different array of numbers for different positions. So now when you look at the final embeddings of this token, so assume that this is the token, this is the token embeddings of the same token, we are getting a different embedding vector, because it is considering the position. So this is called absolute positional embedding. There are different techniques. One is absolute, then there is a relative positional embedding, where the focus is on relative position between the tokens, not the exact position of the token. So there are different techniques, different models, but we are going to use absolute positional embeddings. And in fact, if you want, so let me just share you one nice animation. I think this is a little old, but I guess this will give you an intuition of how these random array of numbers can be generated. Although there are very sophisticated techniques available these days, but this was one of the previous technique by using Fourier transform. So let me just share it with you, how this works. So imagine that you have just 4 dimensions. That means you are representing every token into an array of 4 numbers. So what you can do is, what you could do is, you generate 4 different signals or 4 different samples using Fourier transform. Or basically, the way that you can intuitively think of this as, let's say you create 2 functions of sine, 2 functions of cos, right? And with different frequencies, and it will look up like this, right? And on the x-axis, this you can consider as the length of the sentence, or the position of the sentence, or of the words in a sentence. So starting with position 0 to position 100. That means here we should be able to generate the positional embeddings of any string which contains 100 tokens, right? And the way that we will generate is, all these are random functions, right? Not random functions, but different functions of different frequencies. And the number of functions that you are going to use will depend on the number of dimensions. So in this case, it's 4. So now, if you want to find out the positional embedding or positional encoding of the 30th word, you can just look at the amplitude of all these 4 signals at the position 30. That's all. So in this case, at the 30th position, the numbers happen to be -1, 0.25, 0.91, 0.25. So you can consider this as the positional embedding of the 30th token. Similarly, the 40th token, if you want to do, it will be all the amplitude of these 4 signals at this position, right? So this is one of the technique that you could use to find out the positional embedding of all the tokens. And then what you do is, let's say the 30th word is fish. So fish will have an embedding, right? And the embedding length would be 4, of course 4, because that's why we are using a positional embedding of dimension 4. So what you will do is you will add the embedding of fish along with the positional embedding of fish, which is happen to be, let's say, in the 30th word in the sentence, and that will become the final embedding of this token fish. Right? So now that embedding of fish contains not only the information of fish but also the position of fish in the entire context. Okay, so that is one of the techniques that people have used earlier in training transformer based different architectures and transformer based models. But at this point in today's time, we have many more sophisticated techniques, but the core idea is this, that you need to come up with an array of numbers which represents different positions, and you just add that with your token embedding. That's all, and you will end up getting the final embedding of your tokens. So for this example, and now let's go a little more real. Previously, we used a vocabulary size of 6. Now let's use the vocabulary size as 50,000 or 257, which is the vocabulary size which GPT-2 model has used. And now we are using an output embedding size of 256. That means every token will have an array of 256 numbers, right? So that is the length of the embedding vector. So here we are creating the token embedding layer, and here we are again loading our data, but in this case we are using a batch size of 8. And now if we just see the token IDs, we will see there are a batch of 8 tokens, a batch of 8 samples, and each is of size 4 because the max length is 4. So what is happening here? In this case, we have total 8 samples, and each of these samples contains 4 tokens. These are the token IDs of different tokens. Now each of this token, we want this to convert into a vector of size 256, right? So each of this token will have a vector of 256. So let's see how we can do this. So what we can do is we can just say token embedding layer, and we can parse this input, because token embedding layer is the layer that we have created here using torch.nn.embedding, and we will just pass this input, right? So before I execute, let's think about the size of this token embedding. So if you see this, the size of this input is 8 cross 4, right? So it is 8 cross 4, right? So now we want each of this token to get an array of numbers, and the length of that array is 256. So that means this should change into, we will have 8 as a batch size, 4 because there are 4 tokens, but each token will be of 256, right? So this is what the size that we expect. So let's execute this, and sure enough, we are now having a tensor of size 8 cross 4 cross 256. Okay, so the last thing that we need to do is we need to add a positional embedding, right? So far, whatever we have done this before as well, nothing new. The only different thing that we did here is we increase the vocabulary size and we increase the output dimension. That's all. But we have not done anything for positional embedding, right? What we were discussing for last couple of minutes. So at the end, what we are going to do is we are going to create the positional embeddings, and the positional embedding size should be same as the size of the output dimension, right? And we are giving the context length as the same as the maximum length. So in this case, we are considering only 4 tokens at a time. So that means we need to have the positional embeddings for 4 tokens. And that is what we are going to do using again with this embedding layer. And in this case, we are saying that we should have a context length of 4 and the output dimension is 256. So if we execute this and then if we find out the shape of the positional embedding, it's 4 cross 256 because there are 4 positions and each position should have an array of 256 numbers. So now that we have the positional embedding and we also have the token embedding, the exact input embedding would be just the addition of these two. That's all. And that's the reason that we need to have of these two of same size so that we can create this final input embedding. Right? So if I execute this, you will see that the embedding size is still the same as before, like what we have seen this before adding the positional embedding. But now this input embedding contains the positional information of each token. At this point, if you look at it, we have covered a lot. So we started off with plain text. We learned how we can tokenize the text. We also learned how to create this token IDs. And then from this, we learned how to create this token embeddings. And finally, we need to add the positional information of each token in that context. Like in this example, the context size seems to be 5, 1, 2, 3, 4, 5. So all these positional embeddings represents each token at a certain position. Like this is the positional embedding of token number 1, token number 2, and so on and so forth. And once we add that with our token embedding, we get the final embedding of our input text. Okay, and now we can use this input embeddings to train our transformer model, or our, in this case, it's a GPT based decoder only transformer model, but you can think of it as any LLM or any transformer based model. So we will take a pause here, and going forward, we will try to learn how we can use embeddings in multimodality and also multimodal RAG. And we will also touch base on different embedding models that we have. We are going to use Amazon Titan embedding model in one of our demo. And this should give you a good overall idea of how text are being treated by a large language model. So next time when you go and open ChatGPT or any of the application backed by LLM and ask a question and you get a response, you know what is happening under the hood when you hit enter and the text goes and you get a response back. So you know what is happening under the covers. Okay, I would highly recommend that you go over the GitHub repo and then play around this notebook. All right. Now that we have learned about embeddings in NLP or embeddings in large language model, and we understood that why embeddings are so important and how it is an integral part of your NLP based application, we can dive deep into different embedding models and see how we can use them on Amazon Bedrock. But before we dive into a specific embedding model, let me tell you a brief about Amazon Bedrock in case you haven't used that service on AWS. So Amazon Bedrock is a fully managed service on AWS, which enables you to access different large language models or different models from different AI startups. Be it Anthropic, be it Mistral, Stability AI, and so on and so forth. So what you can do with Amazon Bedrock is you don't have to manage and get different API keys from different model providers. You can access all these models with just 1 or 2 lines of code change and toggle between one model from another. Right? And we are going to see that how we can implement that in the code. But just to give you a feel of what are the different functionalities that you can get from Bedrock, let me show you in the UI. So I have already logged into my AWS account, and if I just search for Bedrock, you will see there are different options on the left hand side bar. So you can see there is the getting started, where you can just click on different model providers and select the model of your choice and get started with that. And you can also do custom model, meaning you can do fine tuning of your pre-trained model. You can do model distillation. So this is something which we have recently announced during the 2024 reInvent. And we can also do continuous pre-training. Not all the models are available for fine tuning or model distillation or continuous pre-training, and we will see how to determine which model is available for fine tuning or model distillation or continuous pre-training. But keep this in mind that not all models can be fine tuned or customized. Okay, but Amazon Bedrock is not just for accessing different models, but it gives you different offerings. So fine-tuned model or customizing your model is one of the option that you get apart from accessing different models under the same umbrella. We also have playgrounds where you can select chat and you can select any model of your choice. And once you select that, so let's say if I select Nova Pro, which is the latest model that we have announced, you can just select that model and start asking questions, or you can start writing your prompt. So next to Playground, we also have different builders tool. These are the tools which are available on Bedrock, and these are the tools which will enable you as a software developer to build AI enabled software. Few of the options that we have is you can use agents, where you can create an agent by selecting a foundational model, and you can add more real-time actions that the agent should take. And you can also connect knowledge base, and we are going to talk about that in the last section when we build an end-to-end application for insurance management, wherein we will discuss what our agents are, how it is different from function calling, and we will use agents with knowledge base, which is a RAG based solution on Bedrock. So that is what we can see here. We have knowledge base, which takes care of creating a vector database, embedding your data, automating the entire data ingestion pipeline, and so on. So I don't want to spend time on this because I will go deep into this in the next section once we start our multimodal RAG embedding section. But this is also something that you will get on Bedrock. And apart from that, we also have prompt management, guardrails, and so on and so forth. So at its core, Amazon Bedrock is one service, but it's the way that I think about it is it comprises of many different services, small services and features and functionalities, which enables you to build smart application using large language model. And it's not just about Amazon's own model, but this is the place to go for to explore different models without worrying about API keys from different model providers. Okay, so before we even look into any of the model, the first thing that we have to do is we have to make sure that we have the model access for the model that we are looking for. So if you see here, we have different models from different model providers, and you see that whether we have access or not. So if you're logging in for the first time, most likely you will see you don't have access. So in that case, what you have to do is you just have to go up and click on modify model access and select the model which you don't have access, or the model that you would like to have the access. Just click on that and click on next, and then submit the request, and you should be able to get the model access in some time. Most of the time it's very immediate, but in few of the cases it might take some time. But this is the first thing that you need to do to get the model access. Once that is done, you can access these models through SDK and get started with it. Okay, so that is what we are going to do next, how to access these models through SDK. Okay, so lastly, I want to show you something that there are different types of models and there are different modalities. So if you see here, this is the model catalog. And since we have completed only embedding so far. If I click on embedding, you will see that these are the 5 different embedding models that are available. Titan text embedding version 2, Titan multimodal embedding, Titan embedding G1 text, and Cohere multimodal embedding or multilingual embedding, right? So in this section of the course, we will use a Titan embedding model, and we will see how we can access them using Python SDK. Okay, so let me go back to my notebook. Okay, so I have opened a notebook called Embedding with Bedrock, and this is located under the same folder which we used in the previous section while discussing about embedding for NLP. So this is the notebook that we are going to refer in this section. Okay, all right. So just a quick recap of embeddings. So we learned about how embeddings work internally and how we generate those array of numbers for a specific input token. So now what we are going to do is we are going to use a pre-trained model which has been trained in a similar fashion during its pre-training. But now that we have the model available, what we can do is we can simply send our text and we can expect an array of numbers. Now the dimension of this array of numbers is something that we can select, and different model providers have different options, and we will see what Titan text embedding offers us. Okay, and this is the documentation of Titan text embedding model. So if I just click on this, I guess I've opened it in a different tab. Yeah, so this is the home page of the documentation for Titan text embeddings. And as you can see here, if I just scroll down, so this is the model ID we need to use when we access through SDK. And it also gives you some of the information of this model. For example, as you can see, it can take maximum of 8,192 tokens. So that is the maximum length of input token. So if you give any input which contains maximum of 8,192 tokens, it will generate one vector or one embedding. Right? So that is a limit that you should be keeping in mind, because let's say you have a huge chunk of data, and once you tokenize that, you might end up seeing that, okay, this contains a lot of token, more than this, right? So more than 8,192 tokens. So in that case, it won't be able to generate one vector. So in those cases, you have to typically chunk the text in the first place before giving it to the model. Okay, and this is what I was talking about. So you can change the output dimension or the output vector size. By default, it's 1024, but you can always have a smaller vector length. So that means every input token will be converted into 384 array of numbers. So when we discussed embeddings in the previous section, we learned that for a given model, if we have a smaller representation, that means we are discounting different features, right? So a model which a higher dimension is likely to be better with respect to a smaller dimension, because higher dimension always captures more information. And the assumption that we are making is that these informations are all unique, right? So this is something that we need to keep in mind. So it's not that if a vector length is doubled, we will get better information. Although that is most of the time it would be the case for any pre-trained model, but keep in mind that these information should not be duplicated. All right, so these are the few of the information that you should keep in mind. And whenever you look into any model, it's always good to look into these details, like what the model is capable of, so that once we get into the implementation, we can take the right decision. Okay, so now imagine that we have a document. We will use an embedding model, and this embedding model will generate an array of numbers. And the reason that you see a lot of vectors here is because we have lots of documents on the left hand side. So assume that each document contains less than 8,000 tokens, in that case, every document can be converted into one vector. But in case the document contains more than 8,000 tokens, in that case, you need to chunk that. So at this point, you need to chunk the document or split the document in a smaller chunks. And this is where frameworks like LangChain comes in, which makes it very easy to chunk your document. But LangChain is not the only framework. You can use many other frameworks, but essentially these are the functionalities of different LLM-based framework. So let's get started and let's see how we can use a Bedrock model using Python SDK. So here we are importing Boto3. So Boto3 is the SDK in Python to access any AWS resource. So once I import, what I'm going to do is I'm going to create a client object and for Bedrock and one client object for Bedrock runtime. So this might be a little confusing why I'm creating two different clients, but the way that you should think about it is this Bedrock client is kind of the control plane. Right? So if you want to know what are the models which are supported by Bedrock, if you want to know what are the provisioned model that you have in on Bedrock, or what are the fine-tuned model that you have on Bedrock, so these all are the information at the control plane, right? So this is not specific to giving a prompt to a model and expecting a response, right? So which is the job of Bedrock runtime, right? So if you want to use any control plane information, then we have to use the Bedrock client. And when we actually use a model, specific model, then we have to use Bedrock runtime. So let me show you how you can use this client. So I have this Bedrock client, and now if I want to know which are the models available under Bedrock, which we have seen in the UI, but let's say through SDK, if you want to see, I can just use this list of foundational model function, and it will give me the response with all the model IDs. So if you see this is the Titan model, and if you see, it also tells you what is the input modality and what is the output modality. That means what type of input it can take and what type of input it can generate. So this method is very useful to actually know what model is capable of. And if you see here, I was telling you in some time back that you cannot fine tune all the models, right? And you need to check the documentation to know which model can be fine tuned. And this is the option you should look for, this key called customization support. So if it says fine tuning, then you are sure that this particular model, in this case, it is the Titan image generator model. So you can fine tune this particular model. But this is how you can check before you start the fine tuning, that which are the models are available for fine tuning. So this is a very verbose output. So let's say if you want to see which are the list of models, I just wrapped it around a list comprehension. What we are doing here is exactly the same API call, list foundational model, but we are just looping into all these models and capturing the model summary. And from there, we are just taking the model IDs, which is this line, right? So we should get all the model names in the output, and we are able to see all the models which we have. But it is, again, it's a very long list. If you want to see just the embedding models, we are refining the code even more further by just putting a condition called embed. If within the model name, if we have embed, then it should be an embedding model. And how do I know this? I just looked into all the embedding model, and I realized that this is one of the things which we add in the model name itself. So if you see this, we have Titan models and we have coherent models, and that is exactly the models that we have seen in the UI as well. So so far, what we have used is we just used one single API called list foundational models, and that is also in the control plane. But now let's see how you can actually generate the embeddings, right? So which is the most important thing. So it's pretty straightforward. What we have to do is we have to just put our text, whichever is the text that we have. So in this case, this is going to be the prompt. So let's say in this case, our prompt is, hello, thanks for joining. I hope you are learning something new. And now you can simply call this model. And in this case, we are going to use a Titan embedding text model version 2. And we can simply run one single API called invoke model. So Bedrock runtime client is something that we have already created, and we can just use this method called invoke model. And in this, we just have to provide the model ID and the body. So the body is nothing but the exact information that we need to pass to this API. So this is the body of this invocation. And if you notice here, what we have given within this body is our prompt, right? So that is the input text. We can also mention the dimension, as we have seen earlier. Let me just show you again. This model provides the output vector in three different sizes. One is 1024, another is 384, and 256. So by default, if you don't provide anything, it will be 1024, but you can always change the size of the embedding. So let me go back to the notebook, and here the dimension, we have mentioned this as 1024, but even if I remove it, it doesn't matter. It will work as it is, okay? And it will generate a embedding of size 1024. That's all. And there is an option called normalize, and I'll talk about it next. So if you notice here, the only thing that we have done is just provided this model ID, right? So let's say if you want to test with a different model, all you have to do is you just have to change this model ID. So you can pick a different model ID, let's say this Cohere, and you just put the model ID here, and you just have to check the documentation that what is the input structure of this model, and just change this a body. That's all, right? And then you can just invoke the same API invoke model, and you can get the embeddings. So this is the most powerful point about Amazon Bedrock, that you don't have to worry about different model providers, different API keys, and all of that. You can just change one line of code or just a couple of line of code. I say a couple of lines because in many times you might have to change the structure of your body, because different models expects the query or the prompt in a slightly different way, and that's why you might have to change one or two lines of code, and that's all. Okay, so now let's execute this and see what we get. So if you see here, we got a long vector, and we just printed the first three embedding and the last three embedding numbers. But if you see the length of this embedding, so let me just run this. So if you see the length of this embedding, it should be 1024, right? And in fact, if you just change this to 256 and execute it again, and then if you see the length of this, it should be 256. Okay, so that's about how you can generate an embedding of your text. Now, once you have these embeddings, you can embed all your text data, which we are going to see in the next section when we dive into a RAG. But once you have these embeddings, you can store that in an embedding in a vector database, which can store all your embedding, which you can use later on for retrieval. And we are going to look into that later in this course. Okay, so that's about generating an embedding. And there is an option called normalize, which I have not talked about yet. So let me tell you about normalize and why it is important. So normalization, or normalizing a vector in general, it means that you are doing some processing of the output vector that it generates. So normalization is a process of scaling, so that the output vector that you get, the end vector, the final vector that you get, the unit length is 1. Now, this may not be that appealing in the first place. You may think that, okay, what is the point of this? But this is very useful in many of the applications. So it is useful to ensure that all the vectors are in the same scale, right? So if the length of the whole vector is 1, then it is assured that all the vectors are in the same scale. So you might embed different vectors. If you don't use normalization, then embedding of different vectors can vary widely. But if you normalize it, you are always sure, or you are always making sure that all of your embeddings are within the same scale. And this is very important in the context of machine learning most of the time, and not just in NLP, but we do normalization, standardization during the pre-processing and post-processing of our data. And specifically, this is very useful for retrieval purposes, and that's why this is used as a default. So let's see, how you can use a normalized vector when you generate an embedding. So let's say this is the text. So we have just taken one text, and now we are using the same model, but in this case we are changing this option of normalization to true. Right, so normalized is true. So in this case, I expect the vector to be normalized. So let's run this, and we got a long vector. And to check whether this is normalized or not, we can just find out the magnitude of this, right? So that's what we are doing here. So we are just using NumPy. So there is a submodule within NumPy called linear algebra, or linalg, and we can call the norm function and pass on the embedding. And if I run this, you will see that the length of this is 1. So in fact, if I just use this in my previous embedding, right? So let me just call this, and we will see. So let me just run this first, and now if I just find out the length of this vector, you will see it is not 1. So now if I generate the embedding of another text, so let's take this example. So let me just copy this, and let me just replace this and run it again. And if I now try to find out the norm of this, the previous text has a length of 28. So now let's run this, and we will see that this is 24. So you see the difference. So that's why we say that there is no uniformity across different embeddings, and which is not very good when we do any retrieval process, and we use this in any downstream process. And that is the reason we should always normalize the vector, so that all the vectors remains in the same scale. Okay, so that's the whole idea of normalization. All right, so now let's see how the embedding vectors looks. As of now, we have just learned about the array of numbers that it generates, but we have not looked into whether these numbers are actually making sense or not, right? So for that, what we can do is we can generate the embeddings of two similar text and try to find what is the similarity score between two texts, right, which are similar, and evaluate whether this embedding model is doing its job or not. So since we are going to call this embedding model multiple times, so I'm just wrapping these line of code which we have been using over and again for different texts, so that we don't have to write the same code again and again. So it just takes a prompt, and we just use the same model to generate the embedding. That's all. Okay, so you can make this function more useful by taking the input not just the prompt, but also normalization and dimension. But you can always do that when you play around with this notebook. But for this demonstration, we are just expecting the prompt. Okay. So now that we have this function ready, we can have two texts. Let's say the first text is Python is a programming language, and the second text is Java is also a programming language. So now, if you think about it, these two texts are pretty similar. So if we generate the embedding, it is supposed to be very close to each other. So let's try to find out. So here we are just generating the embedding of two vectors, and we are using the cosine similarity. So we are just creating the dot product between two vectors, and then we are just dividing it with the magnitude of both the vectors. That's all. It's a standard formula to get the cosine similarity. And we provide both the text 1 and text 2, and let's see what is the cosine similarity of these two vectors. So if you see this, it's around 0.34, right? So whether this is similar or not, how would we know? Let's try an example which are pretty much orthogonal, right? So let's say it's not at all similar to each other. Okay, so let's say let's change this. Let's say first sentence is, let's keep it as it is, and the second is, let's take some example. uh, this is a table, right? So there's no relationship as such, right? Although we have used is a it's in both this text, but in the context they are not very similar, right? So in here we are talking about table, and there we are talking about programming language. So let's see the cosine similarity. So it's very less, right? But although it's not very less, because it is still talking about something, and this here also it is talking about something. But if you just give something very random, so now you see this, it's pretty less. It's minus 0.01, because they are quite orthogonal to each other. It's no semantic meaning between these two. Similarly, if we have some other text, so let's say in this case it's have a text called it's a sunny day, and we have another text called it may not be raining. So these two are related, but text semantically they are related. If there is no if it is a sunny day, it's very likely that it will not rain, right? So we expect the cosine similarity of these two should be little close, and as we can see here, it is indeed we have a good similarity between these two. Although there is no exact phrase which is common across two texts, although we have it, but here we have its. But this should give you an intuition that why embeddings are so important, and that's why when you pick an embedding model, that actually determines how good your response would come up at the end of the day in your application. Because the better the embedding model is, it can contain better information, and it can give you a better semantic search result when you use it in a downstream process like, let's say, RAG. Okay, so now that we learned about text embeddings, and also we looked into how you can generate embeddings using Bedrock, in the next section we will start off talking about multimodal embeddings and multimodal large language models in general, and we will see how you can use a multimodal model with Bedrock. Okay. So now that we talked about embeddings in natural language processing or embeddings in LLMs, it's good time to talk about multimodal large language model. So in real world, most of our data doesn't contain only text. So the data can have different forms and formats. For example, it could be an image data, it could be a video data, it could be an audio data, and so on and so forth. So far we have learned how we treat text as an input. We learned about how we embed a text and generate an embedding for the text. But how about multimodality? How about different data types? And this is what the objective of this section, to learn about multimodal models and multimodal embedding models. So multimodal models are an advanced AI system which are capable of processing and integrating different types of data. So that data could be text, it could be image, it could be video, it could be audio, so on and so forth. And if you think about it, it has multiple use cases. For example, image captioning. So imagine that you have a set of images and you want to add a description to that image, which is very much relevant in today's world in the e-commerce industry, where you are coming up with a new product and you are generating a new image for that product, and you want to generate a description of that image. Similarly, if you have ever used visual search on Amazon app, which I've seen rampantly being used, especially in the Western countries, wherein people go for shopping at some retail shop and they just open the Amazon app and they just click a picture of the product that they are looking to buy, and they compare that product's price on Amazon and check the price in the retail shop and take an informed decision. So the way that these systems work is, you take an image, you send that image to the backend system, and the system understands what that image is about, right? And you get the right product as an output. So image search, image captioning, visual question answer, wherein you send a screenshot and you ask some question, or you pass a PDF document which contains images, tables, and text, and you want to talk to that PDF document, or you want to question where you expect the answers to be in that document. And we are going to see one example for that in the next section. So the idea is very simple. We want to come up with a model which can handle different types of modality. Now, before we go ahead, one thing to keep in mind is, when we think about multimodal models in particular, we need to first ask the question, in which side of the model we are expecting the modality. For example, in this case, if you see, the input to this model could be text, could be image, could be video, or could be audio. That means the input of this particular model is multimodal, whereas the output, we expect this to be just text, right? So this is also a multimodal model, but we need to be very specific in which side of the model we are talking about, right? When we say it's multimodal. Similarly, there could be some model which just takes a text, but it can generate text as well as images. So that could be also a multimodal model, but it's just that you need to be very careful that multimodal means what in the context of its input and output. So we know that from the world of NLP, ever since we got the paper called Attention You All Need, which is a transformer paper. I think it was published in the year 2017. Phenomenal paper, which changed the entire dynamics of NLP and machine learning in general. So we know how text can be used for any classification task or text generation task, because we have this new architecture called transformer. So for example, we are passing a text and we expect the transformer to predict whether this text is a spam or not spam. So this is very much a common problem, especially in emails, right? We get a lot of emails and we need to classify whether the email is a spam one or not a spam one. So we knew how to handle text data, and this was powered by transformer based model and this has been worked out in the recent past. Previously also, these kind of tasks were accomplished, but not through transformer, but using different models, different architecture. But in today's world, most of the NLP based tasks can be accomplished with transformers. Now, this was very, very powerful, and researchers and scientists came up with a thought that, okay, if this works with text, how can we leverage the same architecture for vision? And that's how Vision Transformer came into picture, which processes unstructured data by converting the data into a numeric representation. So, for example, now with Vision Transformer, if you give a image as an input, it can also classify what that image is about. Here, if you provide an image of a cat, it can predict it's a cat or a dog. So we basically have two different types of model which are backed by similar architecture, which can handle text and image both. But what we are looking for is one single model which can take text or image, and it should be able to embed our data or represent the data in the same vector space, right? So that is the idea of multimodal model. But the fact here is what we have learned in transformer based model, or when we discussed about embeddings, we learned that when we get a text, we chunk it and we tokenize that text. Now, the first question that might come in our mind is, now that input is an image, how can we transform that, right? So we cannot just tokenize an image just the way we tokenize a text. So let's see how we can do this. So if you recall, in NLP, or when the input is plain text, the way that we tokenize it is splitting that text into small tokens. And we have learned different techniques of tokenization like Byte-Pair encoding. But in this case, for the sake of simplicity, let's consider that we have this text and each word is a separate token. We also add some special tokens like CLS, which is a classification token, which always gets added at the beginning. And then we also add a special token called SEP, which stands for separation token, which indicates when a sentence ends and when the next sentence starts. These are the special tokens, but the way that we tokenize is very straightforward. We just split it based on different tokens. So in this case, it's a word-based tokenizer, but in real world, it's always a sub-word-based tokenizer, which we have seen in the embedding section. And once we tokenize it, we pass it through the encoder layer, because we have the embeddings, and now we can just pass it to the encoder layer of our transformer architecture. Now, this works pretty fine in case of plain text, but how about images? They do not consist of words. So we must come up with a strategy to mimic this tokenization so that we can use the same transformer based architecture, but for vision. And that is where vision transformer comes into picture, wherein when we take an image, we first used a patched image. What that essentially means is we break that image into small patches. And then we flatten up those patched input. For example, here in this case, the original image is this, which is an image of a cat. We used a patch of dimension 3 by 3. That means we split this into small blocks, and the total number of blocks is 9. And then we flatten that input. And the objective here is to tokenize the image such that I can use the encoder component of the transformer. Just like how encoder part of the transformer works for text, we want to use a similar architecture, but for vision. So in this case, we have used a 3x3 patched image, but in the original paper, if you read through that paper, you will see that they have used a 16x16 patch. But the core idea remains the same, that you split that image into small patches, and then you flatten those patches, and that becomes your input. Now, the natural thing to do after this is, just like in text, after we tokenize, we assign a token ID. So in this case also, if you think that each of this patch is equivalent to one token, we may want to add one token ID to each of this patch. However, this may not work in the world of vision. And the reason is, when we think about text, let's take an example. A word, the, might come in many texts, right? Because we are very sure that it's an dictionary word which can come in many other text. But in case of image, if we pick one of the image and if we patched it, and then whatever patch we get, let's pick this second patch, I don't think that we can expect this patch in other images that are available on the internet. So that's why it doesn't make sense to uniquely identify each of this patch at this point in time. And that is the reason we don't use this flattened input and perform the tokenization. So we take this flattened input and then we go through a linear layer projection. So what that means is we take this flattened input and then we add a linear projection. And then linear projection gives us a vector. And that vector we used for encoder. Now, of course, each of this patch, once we perform the linear projection, it gives us a vector, but that vector doesn't contain the positional information of each of this patch. So just like in processing text, here as well we add positional embedding, which I've not seen in this block diagram, but imagine that that positional embedding is also being taken care at this layer. And once we have that, once that linear projection is over, we have an array of embeddings. And now that we have the array of embeddings, we can use the same encoder architecture which we have used in text. So this is the core idea. So we wanted to make sure that we leverage the power of transformer architecture. And we have to come up with a way such that image can be also broken into similar format or similar input space so that we can leverage the same architecture. And that's why we came up with this patched image thought process. So this is what we do. Let's say this is an image. We break it into small patches. So in this case, the image is of size 128 cross 128. So that means it has 128 pixel horizontally and 128 pixel vertically. And then let's say we used a patch of size 16 cross 16. We will have 64 total patches. So now if you pick one of the patch, if you take one of the patch, so one patch consists of 16 cross 16. That means there are 16 cross 16 numbers in this patch. So when we flatten that patch, you can think of this as an array of 768 numbers. Right? So if you just do the maths, it's 16 cross 16 cross 3, it's 768. So each patch got vectorized into an array of 768 numbers. This is what the linear projection is all about. Now you can use this array of numbers and then add the positional embeddings, and that you can use as the embedding of that particular patch. And similarly, if you take the embeddings of all the patches, you will get the embedding for the image. And of course, the weights for this linear projection is being trained during the training process. Okay, so that's about processing an image. And this particular image, as you see, it's a beautiful illustration I've taken from this GitHub repo. I've added the source link in case you would like to dive deep. Okay, so now that we learned about processing an image with Vision Transformer, let's combine all these concepts together and understand how a multimodal embedding model is trained. So if you think about what are multimodal embedding models, is that we want a model which can embed an image of a car, for example, and the text car in the same vector space. And they should be very close to each other, because the semantic meaning of car and the semantic meaning of this image is very similar. So we want an embedding model such that the image and the text represent that image should be close to each other. So we have learned that there are embedding models available which can embed images, and there are embedding models which can embed text. but they are in a different space. So they may not be essentially close to each other if we put them together in the same coordinate system. So the aim for a multimodal embedding model is very straightforward. We expect the model to generate the embedding of a text like this. This is a cat. The embedding of this should be very close to the embedding that the model would generate for an image of a cat. So that is what we want. We have learned that text and image both can be embedded using different models. One may be a transformer based model for text, and another would be a transformer based model for vision. But those two embeddings may not be very close to each other. But we want to train an multimodal embedding model such that the output embedding of the sentence and the output embedding of the image should be very close to each other. Now, how we can do this? So this is where an algorithm called constructive language image pre-training, or CLIP, comes into picture. Constructive language image pre-training, or CLIP. So this is one of the model which we have, which are trained to create multimodal embeddings. So let's see how this whole concept of CLIP works. So in the first place, to train a model which is based on CLIP, we need some training data set. And the data set requirement is very straightforward. We need to have a bunch of images along with its caption. So here, if you see, there is a image of a cat, and we have its respective captions. And now we will create a data set with positive pair as well as negative pair. What I mean by that is, imagine that you have, let's say, 10 images. So I've created a note. So let's say you have 10 images, and 10 images have its own respective labels. Now, what we will do is, with this 10 images, we will also generate more pairs, wherein we can take the image number 1 and, let's say, a label number 2. Similarly, we can take the image number 1 with label 3, and so on. So if you think about it, these all are positive examples where the label is exactly for the respective image. Whereas here, the image is 1, but the label is different. That means these all are negative images. So similarly, we will have another set of image label pair, which is, let's say, image 2 and label 1, and so on and so forth. So in this case, we can have image 2 label 3, and then image 2 label 4, and so on. So if we have 10 images, we can have 10 positive pairs and 90 negative pairs. So this is how we should create our data set, with some positive pairs as well as few negative pairs. Okay, so that is the prerequisite. This is the starting point to train any clip-based model. Okay, so now what we are going to do is this. We are going to have two models. That model will have two parts. One is a text encoder part, another would be a vision encoder part, or an image encoder part. And when we have any text, we will make it pass through the text encoder, and we will look into its embedding. And we have seen how to generate a text-based embedding. Similarly, we will pass the image, and we will make it go through the image encoder, and we will get the image embedding. Now, initially, these embeddings may not be close to each other. So because this is not a trained model yet, but at the end of the training, we expect embedding of the sentence and the embedding of the image should be very close to each other for positive pairs, for all these positive pairs. And at the same time, we expect that for all the negative pairs, the distance between the image and the label should be very far to each other. That means the embedding of this image 1 and the embedding of this label 2 should be far from each other, because they are not related. So with clip, you not only make image and respective text embedding closer, but you also make sure the embedding of dissimilar image and its description are far from each other. Okay, so that's the whole idea or the objective function here for this training process. So the way that we will do it is like this. We will have lots of positive and negative pairs. We will pass it through the model. So we will have the text encoder and the image encoder. We will compare the distance between these two, and then we will compare that with the label. So if the label is positive, we expect the distance to be smaller, and if the label is negative, then we expect the distance to be larger. And we keep on doing this, and we will backpropagate and update the weights of these models, or the text encoder and the image encoder. And during this model, it will optimize, and finally, we will get a model wherein the moment you send a text and the moment you send an image, which is, let's say, in this case, an image of a cat, and the sentence is, "This is a cat," you will find the embedding that it generates for the sentence and the image are very close to each other. And once we have that, we can call that model as a multimodal embedding model, which understands text as well as image. And most importantly, they can put the vectors into the same vector space. Right? So that's the final outcome of any clip-based multimodal model. So one thing to note here is, before we jump into the code, is here when the input is text and when the our input is image, so we expect the model to take both of them, right? So that's the whole idea of multimodality. So there are some requirement from the model which might mandate you to pre-process the image before the model takes that as an input, because every model have a different architecture, different requirement. So most of the time when you have a text and an image, you have to go through a pre-processing, because the image can be of different sizes, right? But when the model was trained, the model might have been trained with a certain dimension, a certain size. So before throwing any image of any size, you might have to pre-process that image before you pass that image to the model. So there are many clip-based model available. To get started, I will show you how we can leverage the open clip model. So for this, we have to install the transformer and Hugging Face library. I think I've done that prior to starting this video, but all the requirement and prerequisite and libraries required for this, I will add that in a requirement.txt file. So before you get started with this notebook, you can just pip install the requirement file, and you should be good to go for all these examples. Okay, so for this, we are taking some image. So I just have a sample image of a dog, and this is the caption. Right? So this is the caption, and this is the image of a dog. Right? So you can imagine that we have a text with its caption, because this is a positive pair, right? Because the caption is also about a dog. So now let's see how we can use a clip model. So now we are not training a model, but we are just leveraging one of the model which was trained based on the architecture that we have just discussed. So in this case, we are just mentioning the model name. So this is from OpenAI, the clip VIT base patch 32. And the first thing that we need to do is load that model weights. So that's what we are doing here. So we have clip tokenizer fast and clip processor. So these are the two functions or class that you have to call before you use the model. So this is from the transformer library. We have clip tokenizer fast and clip processor. So these two are the pre-processors for the image and the text respectively. And this is the model. So as I discussed a while back, before you pass on your image or text, you have to go through pre-processing. And that's what these two instances of this class would do. Okay, so this is a clip tokenizer which will tokenize any text, and this will be the clip processor which will pre-process any of the image. So let me just show you the image. This is the image of the dog, and the caption is a dog sitting on a field. So this is very much a positive example. So if we use a clip-based model, which in this case is an open AI clip-based model, we expect that the embedding of this image and the embedding of this text should be close to each other. So let's try to see this. So first thing, we have to tokenize this input. That is why we have to use this clip tokenizer, and we are passing this caption, which is the text, and we expect the return value would be a tensor, a PyTorch tensor. And if you look at the ID, okay, I think I have not imported this. I have not executed this cell. So let's do that. Okay, so now if I run this, you will see that this has tokenized my input, a dog sitting on a field, into a bunch of tokens. And if you want to see those tokens actually turned into, we can just call this function called, or a method called, convert IDs to tokens. And if you see here, we have the exact text, a dog sitting on a field, but it has also added two special tokens, which is end of the text and start of the text. And if you carefully notice, the token ID of start of the text, this one, this is the first token. The token ID is 49,406, and the last token, the ID of that is 49,407. So I guess the entire vocabulary size of this tokenizer is, I think, 49,408, because it starts with 0. In fact, we can see this. So we can just call clip tokenizer and we can check the vocabulary size. And as you can see, it's 49,408. That means these special tokens, the start of the text and end of the text, are the last two tokens in the vocabulary. And if you remember, when we discussed about byte-pair encoding, we noticed that at the time of training, the first step is to tokenize it or break the sentence into individual words and add this special character /w, right? And that is exactly what we see here. And the reason is it has used byte-pair encoding under the hood, right? So that's the tokenizer that they have used. Okay, so now that we have processed our text, let's see how we can process our image, right? But before that, let's create the embeddings of this text. So far, what we have done is we just pre-processed the text and we got the token ID. But now we will actually pass that tokens through the model. So that's why we're calling this method called get text features. And we are sending it through the model. And if I scroll up, the model that we are using is the clip model, and we loaded this model with the weights of this model ID, okay, which is a OpenAI clip-based model. So let's now generate the embeddings for this particular text. And if you can see, the size of the embedding is 512. That means this text, this piece of text, has been converted into an array of 512 numbers. So now let's try to do that for the image. So in this case, we will pre-process the image. So this is the image that we have seen, an image of a dog. And for pre-processing, just similar to tokenization, here also we are calling clip preprocessor, and we are parsing image in this case. And we are also saying that the return should be a PyTorch tensor. And we expect the pixel values of that image. So let's see the shape of this image. So the shape of this image is, after pre-processing, is 1 cross 3 cross 224 cross 224. So 1 is because it's always in the format of batch size, the number of channel, and the width and the height, or I think height and width. But the first is the first number denotes the batch size. So after pre-processing, no matter what is the size of the actual image, it will be pre-processed to a size of 224 cross 224. Right? So that is the most important thing here to understand. So now if you want to see the pre-processed image, how it looked like with respect to the image that we have seen, which is quite big in size and high resolution, we can simply just perform some numeric transformation, and we can show this image using matplotlib, right? So, and if you see this image looks of less resolution. Intensity of the image is also is quite lower, and the size is also got reduced, right? So this is the image which will be fed to the model, which we expect will generate an embedding, which should be similar to the embedding of the text. Right? And if you are curious what we are doing here, since our image contains this batch size, we wanted to get rid of that, and that's why we use squeeze. And squeeze 0 means we want to get rid of this dimension, so which is the first dimension, that is dimension 0. And then we are just trying to change the representation of the pixels. So the original data that we have after pre-processing in PyTorch, we have the channel and then height and then the width. But in Matplotlib, the way that we can visualize is we need to make sure that the channel comes at the end. Okay, whereas here the channel is at the very beginning. So that's why we are using permute. We should have this order. First should be the height, next the width, and at the end we want the channels. These are nothing but the indexes of the dimension. All right. So now that we have this image, we can use the image embedding model, which in this case, it's the same model, and get the features of this. And if I run this, you will see that this image also got converted into an array of numbers of dimension 512. That means the same model can be used to embed image as well as text. And as we discussed before, any clip-based model or any multimodal embedding model, we expect the embeddings of similar things should be very close to each other. So now let's see how similar these two embeddings are. So in this case, we are simply doing a dot product between the text embedding and the image embedding. And before this, these few lines of code, what we are essentially doing here is we are just normalizing the embedding vectors. And now if we look at the score, we see that the similarity score is 0.28. Now, this shows that there is some similarity, but how would we know that this is actually very close? I mean, how can we interpret this number? So for that, what we can do is we can take a bunch of images and a bunch of captions, and then try to see the similarity across all of them, so that we can have a relative understanding of similarity. So in this case, we are taking three images: image of a cat, image of a car, and image of a puppy. And there are three respective captions for these three images. And what we are going to do is we are going to loop over each image and pair it with all these three captions. So in totality, we will have 9 examples, but out of 9, only 3 are positive and rest 6 are negative, right? So let's see how their similarity scores would look like. So in this case, I'm just looping over all of them, and we are just trying to store the embeddings of images as well as the text. So let me just run this. What we are essentially doing here is just looping over all the captions and looping over all the images. The code is exactly same as what we have seen before. And now we can just use the cosine similarity, which the functionality which is there in the scikit-learn package under metrics pairwise, and something that we have done earlier, but we have done it kind of manually using NumPy. But here, not NumPy, sorry, PyTorch. As you can see here, we are just doing a dot product between two matrices or two vectors. But now we are using scikit-learn. So you can use whatever you feel like. So if I run this similarity matrix should contain all the information. And here we can visualize that. So you can simply ignore the entire code and just print this similarity matrix variable, and you will see the similarity score. But this is just to show the output in a much more visually appealing way. And if you see this, these three images have a very high similarity score with respect to the three captions which they belong to. And all these off diagonal numbers shows the similarity score between, let's say, this car and this text, a pixel image of a cute cat, which is certainly not the case. And if you see this, the similarity score is very low. So this shows that our embedding model is working pretty good with images as well as text. So this is just an example, but you can always try with different multimodal embedding model and see that which one works best for you. Okay, so now that we learned about clip architecture, and we used OpenClip, and we explored that how we can make use of these models to get the embeddings, we might have noticed that there is an extra step before we pass on the input, whether it's text or image, to the model. So we have to pre-process that. Now there are different models which are available. Like there is a sentence BERT, which is an extension of the very famous BERT architecture, and there, if you use the clip model using sentence transformer, you don't have to do that pre-processing or pre-processing of the text or the image. So in this case, if you see, I'm just importing sentence transformer from sentence transformer here, and I am using the clip vision model. And in this case, I am not doing any pre-processing like I've done earlier. Here, I can simply send the images or the text directly to the model, and we can encode this. And once we get the encodings, we can perform the cosine similarity between all these vectors. So here I'm not printing it in a fancy manner. I just wanted to show you, how simply you can look into the similarities between the vectors that the model generates for the image and the text. And if you notice here, the diagonal numbers are pretty high, whereas the off diagonal numbers are very, very low. So it's the same model, but here we are using sentence transformer. So it is doing the pre-processing on our behalf under the hood. So this might be a better approach to use any clip-based model if you just want to experiment with these architectures. So now that we learned about multimodal embedding model, let's look into multimodal model which can generate text. So far, we have learned about a multimodal embedding model which can take image or text and it can generate embedding. But now let's look into some of the models which can generate text, not just embeddings. So if you realized, we have a lot of sophisticated models which are very good for vision, which are vision-based transformers, and there are very good models which are only for text, which are different LLMs which are based on transformers. Now, there is a new paper which got published by Salesforce called BLIP2, which stands for Bootstrapping Language Image Pre-training for Unified Vision Language Understanding. And this leverages the existing models or existing pre-trained models that we already have for images, or called vision transformers, and text, which are different LLMs. So the idea of Blip is very straightforward. They wanted to use the vision transformer and the language LLMs, or the language model, the large language model models, as a frozen model. That means they want to leverage their learning, their understanding, which are already been pre-trained. Now, the only component that they have added in this new architecture is this middle one, which is called querying transformer. So the core innovation in BLIP2 is this Q-former or the querying transformer, which is a bridge that connects a pre-trained image encoder, example, a vision transformer, with a pre-trained large language model. So the Q-former is the only trainable component in the BLIP2 pipeline. And that is what makes it very, very efficient. Because these vision transformer or this language model are already been trained with a plethora of data, right? So there's a large corpus of data which has been used to train this model. So by using this bridge technique, BLIP2 does not need to train the image encoder or the language model from scratch, because it is able to leverage both the vision transformer and the language model. So let's look into this particular building block called querying transformer and see how this actually being trained. So the Q-former contains two blocks. So we are talking about this particular block. We already know that it has a pre-trained vision transformer and a pre-trained LLM. Now let's dive deep into this Q-former block. So this contains an image transformer module and a text transformer module. So the image transformer module interacts with the vision transformer, that means on the left hand side, and the text transformer module, this module connects with the LLM. That means that a text transformer within this querying transformer connects with the large language model, or on the right hand side, which is a pre-trained LLM. So let's see how this works. So imagine that you have an image. As we have already learned, before we pass on this image to any vision-based transformer or the vision transformer, we patch this image, we do the tokenization and send it to the vision transformer. And then the output of this vision transformer will be fed into this vision transformer block within this Q-former. So within this Q-former, as we have learned, that it contains two modules. One is image transformer module, which is this one. And the other module is the text transformer module, which is this one. And we have not completed this image. So the output of this query transformer will go to the frozen LLM. So that's why they said that this text transformer block within this query transformer is connected to the LLM, okay, which we will see next. So the way that this model is trained is by having three different objective function or three different tasks. So the input for this model or the data set that we need is similar to a clip, where we should have images along with its caption, and there could be some positive samples, there could be some negative samples, but we need data set in a similar format as in clip. If I go back here, let's say we have 10 images along with its 10 labels. We have to have some other data set where we have the image along with labels which doesn't belong to those images. So similar to clip, we should have some positive samples as well as negative samples. And the way that we send this training data during the training process is like this. We send this image to the vision transformer and the caption to the text transformer directly. And these are the three different objective functions which we try to adhere to and minimize the loss. And the three different tasks that we have here are image text matching, image text contrastive learning, image grounded text generation. So as the name suggests, the first objective function called image text matching is a classification task to predict whether an image and a text pair is positive or negative. That means if you pass if your data sample or the first data point is a image of a cat, and let's say the caption of that is a pixeled image of a cute cat, in that case, we know that this image and this caption are very much positive. So we expect this objective function to be positive. Similarly, for a sample where image and labels are not matching, we expect this objective function to be negative. Similarly, the image text contrastive learning, the task of this objective function is to align the pair of image and text embedding such that they maximize their mutual information. This is very much similar to the clip contrastive learning. Similarly, the last objective function is to train the model to generate text based on the information extracted from this image. So it's basically generating the text based on the image. And we already have a positive sample here. We know the description should be like this. So we can always have a loss function which can be minimized using what the model generates. So intuitively, we want to make sure that all these three objective functions are achieved, and if we can minimize the loss by adhering to all these three different objective functions, we can assume that the model has now have the capability to extract a very meaningful information from a given image, and that output will be sent through a learnable projection or learned weight to the large language model. So finally, the learned embedding, which is the output of this query transformer, so whatever comes as the output, which will be again an embedding, that learned embedding from QFormer are passed to the LLM. So these learned embeddings are passed through the LLM, not directly, but via projection layer. So that means there is another layer of transformation that we do, and then we pass it on to the large language model. So you can think of this input as a soft visual prompt, not an prompt that we generally give in the form of text, but it's a visual prompt because this we are getting from this input image. And the magic is happening in the middle, wherein we have forced the objective function in such a way that we expect this model to become very, very good at learning visual information. Okay, so to summarize, Blip2 makes intelligent use of existing technology. Here, the existing technologies are nothing but the vision transformer, which is a pre-trained vision transformer, and the pre-trained large language model. So it uses the existing technology by learning only the QFormer, only this middle block, and that works as a bridge between the pre-trained vision transformer and a large language model to accomplish a very powerful vision language understanding and generation. So that's the core about blips. So let's see how we can leverage this using Python. So the first thing that we are trying to do here is if the system is having GPUs or not, or MPS. Since I'm using a MacBook, so I will not have CUDA, but I'll have MPS. So I just want to check this. And in this case, I would like to leverage MPS because I'm going to load some of the blip-based model from Transformer Hugging Face library. So it will load the Blip2 model from Salesforce, which we have. So since it's a heavy model, it would be good to load it on GPU. So here we are loading the auto preprocessor and Blip2 for conditional generation. So these are the two classes that we have to call, and we will pass this as the model ID. So the model ID is Salesforce Blip2 opt 2.7 billion. That means 2.7 billion parameters that we have in this model. So now we will move this model to the GPU, and this method too will do that job for us. We already have mentioned what is the device. So we are with this here, we are creating this model object, and we are moving this model to MPS. So if you are using GPU, it will move the model to the GPU. So this might take some time. So let's give a couple of seconds. Okay, so it seems that the model has been loaded. So now we should be able to use this model. So since this model contains a visual transformer as well as a language model, we can very well see this by just reading this parameter called vision model. So model.vision model will tell us what is the vision model that has been used. Similarly, we can use model.language model, and it will tell us the language model part of this blip2, right? And it will also tell you all the different layers, what are the how the layers looks like, and so on and so forth. So if you see this, they are k projection, v projection. So if you have read through the transformer architecture, you know what this k projection or value projection or query projection means, right? So now that we have loaded our model, let's see how it is able to generate some text for a particular image. In this case, we are taking an image of a car. So this is an image of a car. And if you look at the size of this image, it is 492 cross 512. So that is the size of this image. So now the first thing that we have to do is we need to pre-process this so that we can make use of the blip model. So if we look at the pre-processed output, we will see that this image, which was 492 cross 512, got converted into an image of 224 cross 224. And it has 3 channels, and one is the batch size. So now if you want to see how this transformed image looks like before we actually pass this image to the model, we can use NumPy and pill to print this image or see this image. So let me run this. And now if you see this, the image is pretty small. And what we are essentially doing here is similar to what we have done before. We are changing the dimensions of the image, which here it's a PyTorch object, but we are using the image module to print that image, and that takes an NumPy array. So what we are essentially doing here is we are changing the dimension. We are keeping the channel as at the end and width and height as it is, right? So that's the only trick that we are performing here. And then we are just using min-max scaler so that the features are within this number 0 to 255. These are nothing but the pixel values, if you think about it in that way. Otherwise, if you look at these pixel values, they range differently. If you want to see this, I can quickly copy this and show it to you. So let's run this. It's in float 16 format. But if you look at these image input, you will see that it is actually integer, and we can actually see that. So if you see this, these are all integers, and these integers is between 0 and 255. And that's the reason that we were able to print this image. Otherwise, it would not work. So that is what we are doing here in the min-max scaling. So it's basically a feature transformation, nothing beyond that. So now that we pre-processed an image, let's see how we can pre-process a text. So in this case, let's take an example. So here we have this text as "Thanks for joining this course." So just like in image, we are pre-processing the text as well. And we expect this to be a PyTorch tensor as the return value. And we are moving this tensor to our device, which in this case is MPS, but it could be GPU or CPU in your case. And we are also specifying the D type, which is of float 16. So once we come here, we will get the token IDs. So let me just comment this and run this. And if I just print the token IDs, you will see the IDs of the token or the text basically. So you can ignore the initial tokens, which is all same, because that is kept for images, because this is a multimodal embedding model. Since we are just passing only the text, we are interested to know the token IDs of this text. So now if we just uncomment this, and if you want to see what are those tokens, what are these IDs actually represent, we can simply use convert IDs to tokens, which we have seen earlier as well. And we can see the last few tokens, which these are all for image. The last one is the actual text. Thanks for joining this course. But if you notice carefully, the tokens contains a special character called G dot, which is very weird. And it seems that the space got converted into this particular character. So what has happened is actually it is supposed to be a space. However, an internal function takes this character in certain code point and moved them by 256 just to make it printable. So what we can do is we can simply replace this character with underscore, just to recognize that these are actually spaces. That's all. So now this looks pretty much like the text that we had. So let's explore few of the use case. Like for example, let's start with image captioning. So imagine that you have an image and you want this multimodal model to generate a caption for us. So as before, let's pre-process this image. And this is the output of the pre-processed image. And then if you want to see the size of the pixel, we have seen this before. It pre-processes any input image into a size of 3 cross 224 cross 224, and 3 is because it has 3 channels. And the device is already, we know it's MPS in this case, but for you, it could be GPU or CPU as well. So now we can call this model by calling this model.generate, and we can pass this input. And we can say that generate maximum 20 tokens. And let's see what it generates. So as you can see, it has generated a text saying an orange supercar driving on the road at a sunset. So which very much an accurate description for this particular image, right? So if you notice here, we have passed on an image and we have mentioned what is the maximum number of tokens that we expect. It actually can generate a text with that number of maximum tokens. We can in fact try by increasing the token size. So let's say we expect the maximum token to be, let's say 100. Okay, and let's run this and see what description it gives. So in this case, it is not generating anything more, which is okay. But later on, we will see that how we can pass not only just image, but also text, and we can enforce the model to generate a bigger text. Okay, so let's try with another image. So let's say this is an image, and if you see, this is a black and white image. Looks like a bat where somebody has drawn this with ink, right? So it's not a very straightforward image to interpret. So let's see if this blip-based multimodal model can interpret this. So let's take this input and pass this image just like before. And now let's try to generate the caption. Exactly same piece of code which we have used earlier. And as we can see, it has predicted as a black and white ink drawing of a bat, which is very, very apt, right? So this is the power of a blip-based model, which can interpret text as well as image. And this is one of its use case, that given a lot of images, you want to put a caption to all of those images, right? So this is just one example. Let's look into more interesting example, like question and answer, where we will send some image. Along with that, we will ask some question where we expect the answer is embedded into the image itself, or the answer can be found within that image. So let's pick another image in this case, and we can look into this image. It is the same image of a car. And now let's say we want to have a question as this: write down what you see in this picture. And we are just starting the response. It's basically giving a hint that, okay, your response should start from here. And the answer we expect is from the multimodal model. And we are pre-processing this image just like before, but now our max token is 30, right? So it is not 20 which we have tested before, but now it is 30. So now let's see what the response the model generates. And if you see, the response that it generates is from the answer, because that is where we ended. It says a sports car driving on the road at sunset, which is very much correct. And now let's say you want to ask follow-up question, right? So that means you have to add this response in the prompt itself, which we are doing it manually here, like where we kept this much as it is, just like in the previous prompt, but we just copied the response, what we got from here. So whatever the response that we got from here, we are just adding it. So if you see this portion, this is exactly the same answer that we got from the previous prompt. And then we are appending our next question. So this is not ideally you would do in production-based application. You will use some agentic system, or you will have some memory-based context, which you can get in a lot of SDKs. We will see that in Bedrock as well. But you can use this, use any frameworks like LangChain or Llama Index, which can enable you to build a chat-like prompting with some memory, right? So you don't have to create prompt manually like this. But this is just to give you an example that how you can keep on asking question on an image. So in this case, the follow-up question is, what would be the cost of this car? And again, we are pre-processing this image and asking or sending this image to the model and requesting it to generate the text. And if I run this, you will see that the answer it is giving is almost a million, right? So this might have given you an intuition of how a multimodal model is trained and how you can leverage it in your day in, day out work. And one of the important things that I missed to explain is that in this case, when we process the data contains image as well as the text. So previously we sent only image, but in this case, we want the model to get the image along with my text. So that's why we have this input containing images and text, right? And in the next section, we will dive deep into one of those very powerful multimodal model from Amazon called Amazon Nova, which we recently announced during reInvent 2024. And we will dive deep into different multimodal models from Nova. Then we will dive deep into multimodal RAG, which is an exciting topic. At least I really enjoyed working on that project, and I hope that you will also get some insights about this. With that, I'll see you in the next section on Amazon Nova and multimodal RAG. So in the previous section, we talked about multimodal LLMs, and we also discussed different techniques of training a multimodal model. And in this section, we are going to dive deep into Amazon Nova, which is the newest generation of multimodal models from AWS. So Amazon Nova is a family of models which has the multimodal understanding and creative content generation capability with state-of-the-art quality and unparalleled customization. And on top of it, it provides you the best-in-class price performance with all of these models. So let's look into what are the different models that we have and what are their capabilities. So before we dive in, let me show you the notebook that we are going to work for this section. So this particular notebook called Amazon Nova, you can find this under this folder called Multimodal LLM. I think we used the first notebook in the previous section. So this is the Amazon Nova notebook, which you can find under this section. All right. So with Amazon Nova, we have three different models, and one of the model called Premier we have just announced, and this model will be available maybe in mid of 2025. So let's start with the first model called Amazon Nova Micro. So this is a text only model, meaning you can send a text and you can get a text as an output. So it is not a multimodal model, but it's a very cost effective text only lightning fast model. So if you have a use case where you just have to work with text data or textual prompt, which can be of only text as a modality, you may like to prefer Amazon Nova Micro. And then we have Amazon Lite, which is one of the fastest, most affordable multimodal foundational model that we have. And it can take image, video, and text as an input, and it can generate text as an output. Similarly, we have the Amazon Nova Pro, which is the fastest and most cost-effective state-of-the-art multimodal model that we have. And as the name suggests, it's a multimodal model. That means that it can take the input as text, video, or image, and it can generate text as an output. So these are the three models that we have, which comes under understanding models. And we also have Amazon Nova Premier. As I said, it is not yet available, but it would be available in 2025. And this would be an any-to-any model. That means it can take input as image, text, and video, and it can also generate image, text, and video. So it's a any-to-any multimodal model, which is pretty exciting. So if you are interested in this, you may keep an eye on this in 2025. And then we have some creative content generation model, and this is very, very interesting. And these are the models which can generate images and generate videos. We are not going to dive deep into these models, but if you are interested, I will share some resources which you can go over and learn it from there. And these models are very, very effective. So this has some limitation, like in terms of the duration of the video that it can generate and the type of images that it can generate. But if you are into creative industry, you may like to dive deep into Nova Canvas, which is the state-of-the-art image generation model, and Nova Reel, which is a state-of-the-art video generation model. Okay, so I'm going to share you one link. Let me quickly show it to you. So I think this is the one. If you are interested to know about all these different families of foundational models, you may look up into this page, which covers all these models in a bit more details. With that, let me go back to the notebook and focus on different types of multimodal models that we have, specifically the Nova Lite and Nova Pro, because Nova Micro is text-only model, so that is pretty straightforward, but we are going to focus more on Lite and Pro. So first thing, as we all know, we have to get the access through UI, and we have seen how to get the access, but just to recap, if you have forgotten how to get the access, we can simply go to Bedrock, and then we can just scroll down and come to model access, and here we can select by the model provider. In this case, it's Amazon, and we can select the model of our choice. So I already have the access, but in case you don't have any access, you may like to click on modify model access, select the model that you would like to get the access, and submit the request. Okay, so assuming that you have the access, now let's go ahead and use these models and see how we can actually send the APIs to these models. Again, these are few texts which I have just put in this notebook for your reference, because Since we have multiple options, the natural question that might come up is when to use which model. So this is just a kind of a decision tree which you can think of in the back of your head and decide which model to consider. So micro is very straightforward. It's a text only model. So whenever your requirement is only text, you can go with that. And light and pro is something that you may like to decide based on your use case and the complexity of your use case. If it requires a lot of advanced reasoning and creativity, and not only that, even code generation, then you may like to use Amazon Nova Pro. Otherwise, you may get started with light and see how it is performing with your use case. So, as we know, to use any model under Bedrock, what we have to simply do is we need to create a Bedrock runtime client and specify the model of our choice. So, in this case, I'm creating 3 different variables because I will be using different models in different model invocation. So, I will just refer to different models to their variable names. So before we send an API call and use this model using invoke model, let's look into the API structure or the request structure and how that request body would look like. So since this is an multimodal model, the prompt can contain text, image, or video. So that's why you are seeing that we have a key called content, and it can be of type text, as you can see here, or it could be image, or it could be video. Now, text is pretty straightforward. You just pass on the text. So this is going to be your prompt. And if it is an image, then it supports different types of images. Again, you can refer to the documentation, but I just put it together in this notebook so that you don't have to hop around. But for the latest features or latest support of different images and videos, I would always recommend to refer to the documentation because we keep on updating it as we go along. So in this case, whatever is the image, you can mention that in the format, and you have to send the image in a base 64 encoded format. In case of video, similar to image, you have to mention the format. There are different formats supported like MPG, then FLV, MP4, MOV. So you can mention that. And for video, there are 2 ways that you can provide because video size are typically pretty big. So at times, if the video is very small, you may like to send the video in the form of base 64 encoded string, just like the image. But if the video is very big, then it is recommended to upload that video in an S3 location and provide the bucket name. Amazon S3 is an object-based storage service. If you have never used it, it's just an object-based storage on AWS. So you can upload the image on S3 bucket and provide the location of the S3 bucket. And we are going to see that in the code in a moment. So that's about the content part, like how you will parse your prompt, whether it's text, image, or video. And in the later section, you can always provide different inference parameters, like what is the maximum number of tokens that you would like to generate, what is the value of temperature, what is the value of top P or top K. So these are the tunables that can change the response from the model. So let's look into a few of these parameters in details. The maximum new token or max new tokens dictates the maximum number of tokens that you want the model to generate. So the maximum limit as of today is 5,000. That means the model can generate up to 5,000 tokens. And if you set the value as, let's say, 100, then the model will generate maximum 100 tokens. So depending on your use case, you may like to change this number. And then we have temperature, which dictates the amount of randomness in the response. If the temperature is very high, then the randomness would be more. If the temperature is low, the randomness would be less. And then we have top P and top K. So top P is also called nucleus sampling. So let me explain this with an example. So as we know in LLMs, what it does at its core is it just generates one token at a time. So it picks one token from the entire vocabulary if you think about only text. So what top P does is it takes the cumulative probability depending on the value that we give. Imagine that our entire vocabulary that the model has is just six, right? So there are six tokens, and every time the model generates an output, it would pick one of those six tokens. And let's say my top p value is set to zero point 0.7. Okay, so that's the top p value that I have set. So in that case, what would happen is assume that while generating the next token, these are the probability of those six tokens. So my vocab size is 6. Okay, so this is an example that we are just framing. So in that case, every time it tries to generate a token, it will have a probability distribution across all these six tokens. And for a particular instance, let's say the probability distribution is like this, and it will be always in the decreasing order. So the first token is zero point 0.5 probable, the second token is 0.2, and so on and so forth. Now, when the top P is 0.7, what that means is it will just keep on adding the probability from the maximum one and keep on going, and it will stop at the top P value. So in our case, the first two tokens, the cumulative probability density is zero point 0.7. So what top P 0.7 would do is it will just take the first two tokens. So it will take the first two tokens, and these are the two tokens. Whatever are these two tokens, it will just pick one of these two tokens. So it will completely ignore the rest of the four tokens. So that's about top P. So let's look into other parameters that you may like to change. So the next parameter that we can change is top K, which is again an optional parameter, and it samples only from top K tokens. So if we say top K is 10, then it will just pick the top 10 tokens and it will give one token out of those top 10 tokens. So you can very much put any number in this case. So if you have a very large number, that means you are letting the model select from a large number of tokens. But if you make top K as very small, then you are making the search space, or basically the sampling space, very, very small. Not the search space, but the sampling space, very small. So you can always use top P and top K together, but you should understand what you are doing. But we don't recommend to use top P and temperature together. You can use one of them. And then we have another parameter called stop sequence, which contains the array of strings. And what you are essentially telling the model by setting stop sequence is if you find any of this string which you mention in this array, then just stop. So it's basically a signal which you are trying to give to the model to stop generating the response. So these are some advanced parameters which are very much dependent on your use case, and different people uses different types of settings before they start working with these models. So with that, let's use these models and see how they respond. So here we are creating few variables for system prompt, then our actual prompt, and the inference parameter or the tunables that we have just seen. And we will start off with a synchronous API call. That means we will get the response of the model right away. But there are different techniques that you can call this model apart from synchronous API, which we have not seen so far, but we will look into a streaming API as well, where you will be able to see every token that the model generates, and we can actually work with that as it generates. So let's start with a synchronous API call. So here we are putting the system prompt, dictating the model that what it should behave as. So here we are saying that you should respond to all messages in French. So this is kind of the character that we are injecting to the model. And then we have the message list. So this should contain our actual prompt. So in this case, the role is user, because we as an end user is going to provide the prompt, and the text is this. We are saying that Free Code Camp is a great platform to learn coding and technology in the field of computer science. We expect the model to generate the French translated version of this English text. We are also setting up few of the inference parameters like 300. That means it should generate a maximum 300 tokens. We are also using a top P as 90% or 0.9 and top K as 20. And similarly, we are also having a temperature of 0.7. So as we mentioned before, we should not use temperature and top P together. So I'm going to delete this and we will go with this parameter. And now what we are going to do is we are going to structure this invocation. So this is the reason that we have broken our prompt into two pieces. The system list will contain all the system prompts and the message list will contain all the actual text prompts. So this is the request body that the model will be expecting from the end user. So it should have a key called messages, which should have all the messages. It should have a key called system, which should contain all the system prompt and then the inference configuration, which are nothing but the tunables that we have set. So if you write your code in this format, it would be easier for others in the team to read. You can always use frameworks like LangChain or Llama Index to annotate your prompt or basically structure your prompt in a much better way. But since we are using the native SDK from AWS, which is Boto 3, we are structuring it from our side. But the core idea remains the same, whether you use AWS SDK or any other framework like LangChain. So once this is done, we can call the invoke model API by passing the model ID. And in this case, we are going to use the Nova Lite model, and we can just send our native request, which is the body for this invoke model API. And once we have this, we can load the response and see what the model predicts. So let's execute this. Okay, so I think I have not executed the previous cell. Let me scroll up and run this. Okay, so now if I come down, it should work fine. So now what is happening is it took 1 second or so to generate the response. Since we have used the synchronous API call, it has generated the response all at once and gave us the output. And later on, we will see streaming API where it will stream token by token. So if you notice the response, it has generated the response in French. So I don't know French, so I assume that it is correct. But if you notice carefully, it has not converted or translated this word Free Code Camp into French because it understood that this is a company name or an entity. So we should not translate this, right? So that's how you can use a Nova model. And in general, this is the same structure that you would use for any model for that matter on Bedrock. Maybe this request structure might change a little bit depending on a different AI model provider, but overall, the structure is pretty standard. Now, let's take an example of a streaming API. The format looks exactly the same, but the only difference is now we are going to use the invoke model with response stream. So that's the only difference. Previously, we used invoke model, and now we are going to use invoke model with response stream. And we can have the same system prompt, the same message, and we can always have the inference parameter. So here also, let me just delete temperature and run this cell. So in this case, we are setting the system prompt as act as an creative writer assistant. So that means we are expecting the model to generate something as if she is a creative writer. And we are going to provide a topic. So in this case, we are giving this text as the topic. So a camping trip. And let's see how the model generates the response. And notice here, we are setting the maximum number of tokens as 200. So since in this case, we are using model with response stream, we have to read the streamed chunk or streamed data and process that. And that's why we have this for loop, which will iterate over and read the response from the model. And we are also setting a counter called chunk count as 0, and we will increment that to validate that the model generates maximum 200 tokens. So that is just for our own internal verification. So let me run this cell, and if you see this, the response that it was generating is 1 token at a time. In fact, if I just increase the number of tokens, so let me change it to, let's say, 1000 and run this. You see this, it is generating, keep on generating tokens, and it is getting streamed. So the maximum number of tokens here in this case is 506, which is okay. As long as it is not exceeding 1000, it should be fine, right? So this is how you can use a streaming API as well as the standard API for your use case. So now that we looked into the text understanding of Nova model, let's dive deep into image understanding and learn how Nova model interprets any image. So with Amazon Nova, you can provide multiple images in the payload. So what that means is you can have multiple images in your prompt, provided that the total size of the payload is not more than 25 MB, which is the limit or the maximum size that we have as of today. So you can always pass your image along with your question. And the question could be classify an image or even asking the model to summarize what it sees in that image. So when the Nova model gets your image, it tries to capture the best possible information or tries to extract the best possible information from your image. And in a process of doing that, it automatically rescales your input image by upsampling or downsampling depending on the aspect ratio of the image. For each image, Amazon Nova will first identify the closest aspect ratio. And it could be 1:1, 1:2, and so on and so forth, as you can see here. So let's take an example for better understanding. So let's say your image is of size 800 cross 400, right? So that is the input image that you have. And based on this size, the aspect ratio, if you can see from here, 800 cross 400 is 1:2, right? So that is the closest aspect ratio of the image that we have given. So that aspect ratio will be kept in mind, and then Nova will pick the right resolution. So if you see the resolutions that we have, the right resolution would be 900 cross 450 because that is the closest resolution with respect to the image that we have provided of size 800 by 400, keeping the same aspect ratio. And the aspect ratio of our input image and this resized image of 900 cross 450 is same, right? So what Nova tries to do is during the pre-processing of the image, it tries to make sure that information should not be tampered beyond a point. And this allows Nova to understand image in a much better way. And in this table, you can also see what are the estimated number of token counts with respect to different resolution. So if the size of the image is 900 cross 450, the number of tokens that it will have is roughly around 800. And as you increase the resolution, for obvious reasons, the estimated token counts will increase. All right, so let's pick an example. So we are going to send this image, as you can see, to Nova, and we will try to request Nova to generate a caption. And what we will do is we will request Nova or the model that provide 3 potential titles for this image. Okay, so let's try to run this code. And this is exactly the same code as before, but here, since we are not passing only the text, we are parsing the image as well. That's why we have to have a wrapper function which can convert our image into base 64 string. So that is what we are doing in this few lines of code, where we are opening the image and then we are just using base 64 to encode that data. Okay, so once we have this, we are sending this into this image dictionary, and we are also providing a prompt saying that provide the title for this art, or for this image. And again, we have few inference parameters. Again, let me just delete temperature here, and we can just use invoke model. So let me execute this and see what it generates. So if you see this, it has generated these three responses, which is pretty much accurate with respect to the image that we have provided, right? So that's how you can use Nova model for processing any image. And you might wonder that how I know the structure of this response. I honestly did not know. So what I have done is I have initially printed the full response. And when you do that, you actually know the dictionary structure. You can always refer to the documentation, but the way that I feel we can learn quickly is just to see the response by ourselves and pick the right path to get the exact response that we are looking for. Okay, so that's about one image. But let's say you want to parse more than one image. We learned that Nova supports multiple images provided the maximum size of the payload is within the limit, which is 25 MB. It should be fine. So in this case, we are going to send two images. One is the image of this cat, and another one is the image of this dog. So let's see how Nova model behaves when we add two images. So in this case, we are processing two images separately. You may like to have a wrapper function, which you can call to do the same thing. So I think that is more advisable and recommended. We should not have duplicate codes like that. But since this is a demo, it's fine. So with this, we are appending the content of two images in this message list. And that's why you see two entries to this content, and both are of type image. And then we have the prompt saying that what is common in these two images. So this is a little tricky, right? We are not asking or to put the caption for these two images, but we are trying to ask something complex. We are trying to ask common thing in these two images. So this needs some logical thinking, or rather more reasoning, right? So let's see how Nova model respond to this. So let me execute this and see what we get. So it says that the two image depicts animals, specifically a dog and cat, both of which are pet, and they are both looking directly at the camera. So the response is very, very natural, right? So when I first read this response, I was very happy to see that it was able to understand the image in a much better way, and it was able to correlate with these images. Lastly, let's go over video understanding and see how Amazon Nova processes any video. So just like in images, you can have images of different formats. For video as well, you can have different formats like MP4, MOV, MPEG, and so on and so forth. And the difference is here, you can provide the video in two different ways. One, you can provide the video in the form of base 64 encoded string, provided that the size of the payload is less than 25 megabytes. And this is exactly same as the limitation that we have for image understanding. But if your video is longer, which would be the case in most of the scenario, in that case, we recommend that you upload the video in an Amazon S3 bucket and use that S3 URL to process that. Right? So there are two ways that you can provide your videos. One is using base 64, the other one is using Amazon S3. And when you use Amazon S3, the size limitation of the video is a little bit extended. So now you can have the video of size up to 1 gigabyte. Okay, so that's about the format support and the input methods. And I would always recommend that you refer to the user guide to understand the latest supported file formats and what is the limitations that we have. In fact, let me show you the user guide. So this is the user guide that we have for Amazon Nova. And if you see here, we have a section called Video Understanding Limitations and Video Understanding Example. So I have taken the text from this user guide into the notebook, but it is always good to refer to the documentation because this, we try to keep it updated as we go along. Okay, so let's see how we process the video information. So as you can see here, it says the Amazon Video Understanding capability supports multi-aspect ratio, and all videos are resized with distortion up or down based on the input to a size of 672 cross 672 square dimension before we feed that input video to the model. So that means we do some pre-processing with the support of multi-aspect ratio. And one of the most important thing while processing a video is this: we process 1 frame per second as a sampling rate. So that is the sampling rate that we have. And for any video which is less than 16 minutes, this is the sampling ratio that we use. So what that means is, let's say you have a 16-minute video and we sample 1 frame every second. So the total number of frames that we will have would be 960. So that is very much consistent across all the videos, no matter what's the length of the video. So if you have a longer video, more than 16 minutes, then just to make this number consistent, the frequency of frames per second sampling would be different. What I mean by that is this. So if you look at this table, it will make things very clear. So let's say you have a video of duration 10 seconds. So in that case, since we said you can have 1 frame per second, so we will have 10 as frames to sample ratio. Similarly, if the video is of 30 seconds, then we will have 30 frames. At max, we can have 960 frames to sample. So that is what we will do if your video length is of 16 minutes. But now, if your video length is of 20 minutes, now we cannot have 1 frame per second ratio. We cannot maintain that since that is the max that we can have. So that's why the sampling ratio goes down. So now the sample ratio is 0.75, right? Because we will not take one sample every after 1 second. We might take one sample every after 1.25 seconds or something like that. So we can do the maths, but the idea is this, that the frames to sample is capped to 960. So depending on the duration of your video, we just calibrate. Okay. And just like how we have seen the expected number of tokens depending on the image size or the dimension, here also we are sharing few of the estimated token counts based on your video length. So the more or the bigger or the larger the video is, the larger is the estimated token count. Okay, so that's some internal about video understanding. I don't think you would need to go through all these details when you actually deploy any application or build any application using Nova, but it's always good to read all these details. And one important thing here is, if you read this line, it says that there is no difference when analyzing a 4K version of video and a full HD version. Similarly, because the sampling rate is at most 1 frame per second, a 60 FPS video should perform as well as a 30 frames per second video, right? So this is very, very important. Since our sampling ratio doesn't change, it's still 1 frame per second. That's the max that we can have. So it doesn't matter that you have a 4K video or full HD video, right? So that's very important in terms of understanding how the model analyzes our input video. Okay, so let's go back to our notebook. And just process a few videos and see how it works. So we have a sample video here, which is, if I can just play, it doesn't have any audio, it's just a sample video of 12 seconds. That means when I send this video, when Nova will process, it will have a sample ratio of 1 per second. So total number of frames that it will have is 12. So in this case, we are going to use base 64 based encoding, and that's why we are just encoding the video file, and then the same input process or the same request structure. We have a system prompt, we have the message block, and the inference parameter or the configurations for inference. So here we are providing a text saying that provide a video title for this clip. And the remaining code is exactly same as we have used while invoking this model for images. And in this case, we are using the light model, but you can always try with Nova Pro. Let me execute this and see what we get. And if you see here, it has provided these three responses, which is very much apt with respect to the video that we have. Okay, so this is about processing video using base 64 encoding. Let's see how we can process the same video when we upload it on S3 bucket. So in this case, I have uploaded the same video on this S3 bucket, and we are keeping the prompt as is. There is no change except the fact that here we are just using source as S3. If I scroll up, you will see the source was base 64. So that's the only difference, except that everything is exactly the same. So let me execute this code and see what we get. Okay, so as you can see, it has generated 3 responses, which is very much apt for this video. So that's all for this section. In the next section, we are going to use Amazon Nova and explore how we can leverage Amazon Nova along with LangChain and build an end-to-end multimodal RAG system. In this section of the course, we are going to dive deep into multimodal RAG with Amazon Bedrock, Amazon Nova, and LangChain. But before we get started with multimodal RAG, let's understand what is RAG. And to know that, we need to first discuss about some of the limitations of large language model so that we can better appreciate the importance and value of RAG. So let's say you have some questions about your own organization, and assume that you are the product manager or a CEO of an e-commerce platform, and you would like to know which are the products got the best reviews on your platform in last 15 days. So this is a very specific question which can be answered only if the model have the access to your proprietary data. Or let's say you would like to know something about a recent event. For example, who won the Nobel Prize in Physics in 2024? So if you ask these kind of questions where the answer depends on either your own proprietary data or on a recent event, the LLM or the foundational model won't be able to give you the right answer. And the reasons are knowledge cutoff and hallucination. So these are the limitations that we have with large language model, wherein when we ask a specific question about our own business, where the answer relies on our own proprietary data, the model might generate some response, but it will be an hallucinated response because the model has never seen our proprietary data. It was never available to the model during its training period. Similarly, when we ask a specific question about a recent event, the model won't be able to generate the response because the model is trained on the data set that was available to it till a certain point in time. And when we ask a specific question that has occurred very recently, the model won't be able to generate the response because of knowledge cutoff. So in a lot of the businesses, we may not be able to use large language model as is. And to overcome that, we need to customize our foundational models. Now, there are different techniques to customize any foundational models, and one of them is called fine tuning, wherein you take your labeled data. So these are your proprietary data, and then you fine tune a pre-trained model. And once the fine tuning is done, you can use that model for your production or for your application. Similarly, we have another technique called continuous pre-training, which is very much similar to fine-tuning, but with a small difference that in this case, you need unlabeled data. But in both the cases, you need some degree of expertise within your organization. And most importantly, you need to have a data set in a proper structure or a proper format. In case of fine tuning, you need labeled set of data. In case of continuous pre-training, you need unlabeled data sets. So this is also a challenge in a lot of organizations to even come up with these properly structured data. And that's why we have a third technique, which is actually the topic of this section of this course, called information retrieval, wherein we don't touch the pre-trained model. So we just used the pre-trained model as is, but what we essentially do is we store our proprietary data in a database. We call it as a vector database because we convert these data into embeddings and store those embeddings in a vector database. And then when we ask a question, we don't ask the question directly to the pre-trained model, but we first throw that question to the vector database and we do a semantic search and try to find out relevant chunks which has a high likelihood to get the answer of our question. And then once we have that relevant chunk with respect to our prompt or with respect to our question, we send that question along with the context to the large language model. So now, when you send this question to the large language model along with the context, the model should be able to give us the right response because you are helping the model by providing that context. Right? So let's dive deep a little bit more on this information retrieval part and see how it works. And once we understand this, we will go back to our multimodal RAG pipeline. So let's say we have our raw data, and that raw data could be of any format: audio, image, text, and so on and so forth. So the first thing that we need to do is called embeddings. So we need to convert all these data using any embedding model. And we have seen that in the previous section of the course, how you can create embeddings of your data. And once you have those embeddings, which are nothing but an array of numbers, we need to store these embeddings in some database. So in this case, we will be storing it in one of the vector database. So there are a lot of options that we have in to store the vectors. For example, you can use OpenSearch, you can use Aurora. These are the vector databases that you have on AWS, but you can very well use any open source or any other vector databases like Pinecone and so on. Okay, so once you store your data into a vector database, your data ingestion part is over. So at this point in time, all your data, all your proprietary data is now stored in this vector database. So at this point in time, in your application, when you have a question, you will not ask this question directly to the LLM, but instead we will ask this question to the vector database. So when I say ask the question, it actually means we are throwing the question to get relevant chunks from the vector database. Imagine the way that you should think about it is like this. So let's say I'm a librarian and you have come to me asking about, let's say, what is OSI layer? So I know that this question is about networking. And as a librarian, what I can do is I can go back and I can give 2 or 3 books to you, and I can tell that, okay, go read these 3 books. You should be able to get the answer. So I have not given the exact answer, but I have given some resource which can help him to get the answer. This is very much analogous to this. So when you send a question or when you send a query to a vector database, the vector database will do a semantic search and it will give all the closest match where the system feels that you should be get the answer from these relevant chunks. And now you take this query and the context and send it to the LLM. And now the LLM should be able to give you the right response. If you think about it, there are a lot of things that we are doing here. So we are first throwing this question to the vector database to find the relevant chunk. And once we have that, we concatenate the query along with the context, and then we send it to the LLM. So there must be someone who should coordinate across all these activities. And this is where we have a lot of framework like LangChain. Right? So you don't have to worry about all these internal workflows. So this technique is called RAG, or Retrieval Augmented Generation, where you don't ask the question directly to the LLM, but you first perform a semantic search with your query and the database, and then get the right context. And then you use that context along with the query to get the right response from the LLM. So that's about RAG. And now that we got a basic intuition and understanding of RAG, it's a good time to dive deep into multimodal RAG with Amazon Bedrock, Amazon Nova, and LangChain. But before we start, I guess I forgot to share a couple of resources in the previous section. So I just thought to spend a couple of minutes sharing those before we get started. So one of the book that I would strongly recommend you to read is called Build a Large Language Model from Scratch by Sebastian. This is a wonderful book if you want to know how to train or how to pre-train a large language model and how to fine-tune a model. So this is a very, very good book. It's an easygoing book, so it's not very complex. In fact, we have covered chapter number 2 when we discussed about embeddings. So I would strongly recommend you to go over this book. The other resource that I would request you to look into is this book called Hands-on Large Language Models by Jay Elmar. So he's also a very popular author and an expert in machine learning. And I used this book to build the content of multimodality. In fact, we have covered chapter number 9 in this book, in this course, in the previous section. So these are a couple of the resources that would help you to get a better understanding of how LLM work internally. Right. So I just thought to share it with you because I missed to share these in the previous section. So before I could forget, I just thought to share it with you. All right. So let's get back to our topic. So now that we have talked about RAG, let's discuss how we can implement a multimodal RAG system. So imagine that you have a data set where the data contains images, texts, and tables. Because in the real world, most of our data that we encounter doesn't contain only text. So in this case, we will assume that we have a bunch of PDF files, and those files contains text, images, and tables. And what we are essentially targeting to do is we want to build a system such that we can ask questions about that PDF file. So imagine that we have a file which contains images, texts, and tables, and we want to ask some question where the answer lies in one of the image or one of the table. Right? So we need to build a system which can help us to get us the answer from that kind of complex data. So the first thing that we would like to do is we would like to extract tables, images, and text from the data. And there are multiple frameworks and multiple tools available to do that. In this demo, we are going to use one of the framework called PyMU, but you can always use some other framework like Unstructured, and you can even build your own filters and extract that information. So once we extract these images, tables, and texts, what we can do is we can use any multimodal embedding model to generate the embeddings of these images, tables, and text. And we have seen a few of the multimodal embedding model from Amazon called Amazon Titan. The Titan embedding model is one of the multimodal model that you can use, but there are other multimodal model available in the industry as well from a few of the AI startups like Cohere. So you can pick any of the multimodal model and convert these images, text, and table into embeddings. And once you have that, you need to store that embeddings in some vector database, as we have seen some time back. And once that is done, we are kind of sorted with our data ingestion. So whatever data that we have, we first extracted the images, tables, and text. Then we used one of the embedding model to generate the embeddings, and then we finally store those embeddings in a vector database. So once this task is over, we can let the user ask some question. Now, when we ask a question, the first thing that we need to do is we need to perform a semantic search within this vector database. And the vector database will give us some relevant chunk based on our query. And once you get that relevant chunk, you can pass on these chunks along with your query to a multimodal LLM. And the reason that we need to use a multimodal LM here is because of the fact that your relevant chunk could be a chunk coming from an image, or the chunk might be coming from text or a table. So since the input can contain image, text, or table, we need to use a multimodal LLM. So this is one of the option to solve this problem. And that's why we call this as option one, which we are going to implement in this notebook. But there are other options available. As you can see, option number 2 and option number 3. So let me briefly talk about option number 2 and option number 3. So as far as the data ingestion is concerned, it's exactly same. So we first take the data, we use some tool to extract images, tables, and text. And then in the first option, we used a multimodal embedding model to generate the embedding. But in this case, we are not going to do that. What we are going to do is we are going to use a machine learning model which can convert these images, tables, and text into their respective summary. So there are a lot of models available which can take an image and create a summary, or rather create a caption, or generate a description of the image. Similarly, there are a lot of models available which can take a text and summarize that text. So we will use one of those model, and then we will generate the summary of the image, summary of the table, and summary of the text. And once we have those summaries, then we will use a text-based embedding model to generate the embedding. So the difference here is we are using a text-based embedding because all the data that we have are text, because we are generating the summary in the first place. That means we are leaving the raw data behind, right? So once we have the summary and its embedding, what we can do is we can store the embedding of those summary in the vector database. So the difference here with respect to the option number 1, which we have just talked about, is that in this case, we are not storing the raw data. We are storing the summary of our data. And what we would also like to store this metadata, so that in case we want, we can go back to the raw data at later point in time, where the metadata will contain information about the summary and its raw data, right? So you can think of it as, from an implementation standpoint, you will have a dictionary where the key would be the actual entity and the value would be the summary, or the other way around. You need to have that hash map stored somewhere. And once you have that, then what you can do is you can ask a question, and then that question you will first send it to the vector database, and the vector database will perform a semantic search with all the summaries that it has, and then it will give you the relevant chunk. Now the relevant chunk is also a text because it's all summary that are stored in the vector database. So ultimately what you will have would be the summary and the exact question or the prompt. In this case, you can just go with any LLM. You don't need to have a multimodal LLM because your input is always text. So this is the difference with respect to the first option, where we need to have a multimodal LLM because the context could be an image, text, or table. But in this option, context would be always a text-based summary, because the summary could be the summary of an image, summary of a text, or summary of a table, but we are not using that raw data here. So that's why we can just settle down with a regular LLM. Now, there is a third option that we have, which is very much similar to the second option, but the only difference is when we perform the semantic search, we will get the summary, but we will not send that summary for the actual answer or the actual response. What we will do is we will take that summary and we will go back to that dictionary or the hash which we have stored, and we will try to find out the actual entity for which we have extracted the summary. For example, let's say you have a question, you ask that question to the vector database, and the vector database has given you few chunks, and those few chunks are the summary of an image and summary of some text. Now, what you will do is you will not send those summaries to the LLM. You will go back to the dictionary that you have saved before, and you will try to find out whose summary are these. So you will exactly find out the image, you will exactly find out the text, and then you will take that text and image along with the prompt, you will send it to the LLM. And since in this case the input could be an image or a text, we need to use a multimodal LLM. So in option number 3 and option number 1, in both the cases, to get the final response, we need to use a multimodal LLM. But the only thing that we are doing differently here in this option number 3 is that we are making the search based on the summary. And that is very much helpful in a lot of use cases wherein you might have your data set such that there are a lot of duplicate data. So in that case, when you summarize in the first place, you can optimize in terms of space usage, as well as you optimize the search space when you perform a semantic search. So the way to think about this is, in the option number 3, we are using summary just for searching. And once we get the relevant chunk, we are not using that summary anywhere to generate the response. We are going back to our hash table and finding the actual raw relevant chunks and use them in our final response. Okay, so we are not going to discuss about option number 2 and option number 3. We are going to discuss about option number 1 with the implementation. So first, we are going to import few libraries, and specifically, we are going to use Tabula. So this is a library that we are going to use to extract tables from a text file. Then we are going to use PyMU PDF to extract images from the PDF. And then, of course, we will use LangChain to process the text data from the PDF. Okay, so let me execute this cell. So once we import all the libraries, the next thing that we need to do is load the data set. So in this case, we are going to use a PDF file, which is nothing but the research paper called Attention is All You Need. And what we are going to do is we are going to download this paper from the internet. And if you notice, this file got downloaded under the data folder. So let me show you the notebook location and the data folder location as well. So This is the same GitHub repo which we have been following throughout this course. And this is the notebook that we are going over now. And it has created a folder called data. And this is the PDF file that we have, which contains 15 pages. Okay, so we have downloaded the data set. Now, the next thing that we are going to do is we are going to extract images, we are going to extract tables, we are going to extract text from this PDF file. Now, these are a few of the wrapper functions that I have, which I will go over in a moment. But let me show you how we are going to process this data set. So we are going to use PyMU PDF to read the file and extract the images. And the first thing that we are going to do is we are going to create a bunch of directories. And this is needed because we need to store all these information, all these extracted images, extracted tables, and extracted text, and store it somewhere. So we are going to create different folders. And if you look at this function, it creates an image folder, it creates a text folder, and the table folder. So these are the three different directories that we are going to create in which we are going to store all this extracted information. And we are also going to create a folder called page images, wherein we will also store each page of the PDF as an image. And the reason that we want to store this is at later point in time, when we try for a semantic search, we will get some relevant chunk. And let's say the relevant chunk contains a text, a paragraph, or a chunk of text from page number 10. So what we can do is we can, at the end, not only just send that chunk, but also we can send the entire page from where that chunk or from where that text is coming. Because we know that if a question can have the answer in a particular chunk, it is very likely the content on that page will also have some relevant information. So basically, you are giving more information to the final LLM to generate the response. So that's why we are just storing every page as an image as well, right? So this is kind of optional, but we are doing it in case we need it later on in our pipeline. Essentially, we are creating different folders for all these different entities. Okay, so once we create separate folders, we are creating an object called recursive character text splitter. So this is a functionality or a class within a LangChain which can help us to process any text data. So here, what we are going to do is we are going to extract the text from the PDF with a chunk size of 700 with an overlap of 200. So what that means is we want LangChain to chunk the data based on characters, and we want every chunk to have a size of 700, and it should have an overlap of 200. That means the first chunk will contain the first 700 character, and the second chunk will start from 500 because we have an overlap of 200. So the second chunk will start from 500 till 1200. And then the third chunk will start from 1000 till 1700 and so on. So these are the parameters that you can tune, you can change based on your data, and you can experiment with it and find out what works best for you, right? So there are different techniques that we have for chunking. There are very advanced mechanisms that are available like dynamic chunking. But for this demo, we are just specifying these chunk size. Okay, so this is only for extracting the text. Now, next, before we go over the whole PDF, we are creating a list called items. And this is the metadata which we are creating, which will contain all the information about all the extracted entities that we find. So this will become very clear once I show you how we are appending to this list. But this will contain images, text, and tables along with its exact location and other metadata. Okay, so once we set up this, we can go over the PDF page by page. So that is what we are doing here. We are looping over the PDF page by page, and then we are trying to first find the tables, and we are trying to extract tables, and then we are trying to find the text and extract the text chunk, and then we are trying to find the images and extract the images, and similarly at the end we are just processing every page as an image. So if you go over all these four functions, let's start with process tables. Here what we are doing is we are using Tabula to read the PDF file and extract the tables. And once we have that table, in case it identifies any table, we are appending to the list that we have created. And the way that we are appending is in the form of a dictionary, where a dictionary contains the page number and the type as table and the exact content of the table and the path where we are storing the table. So this is the path within the directory which we have created here, right? So that is what we are doing in process table. Similarly, in processing text, we are using LangChain, and we are just storing every chunk of data and appending it to the same items list in the form of dictionary in the same format. But the only difference here is here the type is text, whereas for tables, the type is table, right? So we have processed the tables, we have processed the text. The last thing that we need to do is processing the images. So we are using PyMU PDF, as I mentioned earlier, and just like before, we are just extracting the images, and at the end, we are appending the image data into this items list. And since we are going to perform embedding at a later stage of time, we are using the base 64 encoding, because when we perform the embeddings, we need to pass the image as an encoded image, right? So let me execute this cell. As you can see, it is now processing the data. And once that is done, we can look into the specific folders and see what it has extracted. So now that it is over, we can get inside this data folder, and we can see that there is a separate folder for images, which contains only the images that it could find within the PDF. Similarly, it has a separate folder called table, which contains all the tables that it could find within our dataset. So that's what we have done so far. So we have extracted the text, image, and table from our dataset. And now, if you remember, we have been adding all these entities or all these items into this items list. So if we just want to look into the first chunk, which is of type text, we can see this by looking into the first element. And if you see here, it contains some metadata, like this chunk is coming from page number 0, the type is text, and this is the actual raw text, and this is the location of the text in the folder that we have created. Similarly, if you want to see the first chunk or first item of type table, we can see that as well. And in this case, we can see that the first table that it has encountered is in page number 5, and this is the raw text, and this is the location of that table. Similarly for images. The only difference here for images is that we have the base 64 encoded data for the image. Right? So that's the only difference. Otherwise, all these metadata are similar, except we have different types. Okay, so now that we have our data extracted of different modality, what we can do is we can use a multimodal embedding model, and create the embeddings of these data. And what we will do is, after generating the embeddings, we will append the embedding into the same dictionary. So now every entity within this items list contains a dictionary which contains the key called page, type, text, and path. Now, after generating the embeddings, we will just have another key called embeddings. So let's go over this wrapper function, which just generates the embedding. It's a very simple function. I don't want to go over this because we have seen this multiple times. We are using Boto 3 and we are creating a Bedrock runtime client. And we are going to use the multimodal embedding model from Amazon called Titan Embedding Image version 1. And then we are just checking the type of the input. If the input contains an image, then the request body should have a key called input image. But if the input is text or table, which are literally text only, because table is nothing but text with a certain format, we are creating the body with a key called input text. So this is the reason that we have this if condition, because there are different modality that we have, and the way that the model expects the request of body is little different. So that's why we are just checking whether we are trying to embed an image or a text. And once we have that body, which contains not only our prompt, but also the length of the embedding. Right? So in this case, I guess we are using an vector embedding length of 384, but you can always change and use the length of the vector which the model supports and also what works for you. So once we have that, we are just calling the model using invoke model function, and we are providing the model ID and the JSON body. Right? So let me just execute this, and now let's call this function. So this might look like 30-40 lines of code, but essentially it's just one line. So I have written some wrapper code which will help us to show the progress of embedding. So let me execute this and show you what I mean. So if you see this, as it is generating the embedding, we can see how many text and how many tables that it is embedding and so on. So just for this, we have some line of code here, but essentially we are just calling that function which we have just went over a while back, and we are sending the text along with the embedding length. That's all. So in case of table or text, we are just sending the prompt as text. But in case of images, we are just sending the images as the prompt. Right? So at this point in time, if I just go back to our architecture, we are at this stage. So we have downloaded the dataset, then we used PyMU to extract the images, and then we use LangChain to extract the text, and we also use Tabula to extract tables. So once we extracted all these entities, we also created the embeddings using the Titan embedding, a multimodal embedding model. So the next step is to store those embeddings into a vector database. So let's scroll down and store all the embeddings that we have generated into a vector database. So in this case, we are going to use an open source framework called FAS from Meta. But what you can do is, for your application, you may like to use any other vector database like Aurora, OpenSearch, Pinecone, ApertureDB, and so on. But for this case, since it's a small demo setup, we are just using FAS, which would enable us to create an index in the memory in our local system. So here we are taking all the embeddings from our items list of all the entities, from tables, embeddings of tables, embeddings of images, text, and so on. So we are taking all the embeddings and storing it into this variable called all embeddings, and we are just adding those embeddings in our FAS index. So at this point, once I execute this, I have all my data in the form of vectors in a vector store called index. So that is the FAS index that we have. So at this point in time, we are all set for retrieval and generation. So for generation, we are going to use the multimodal model, which we have seen in the previous section from Amazon called Amazon Nova. So this is just a wrapper function to call the model, and we have seen this structure. So we have a system prompt or system message. Then we have the message content, which would contain our prompt. And then we have the inference parameters like top P, top K, and max tokens. And we have seen all of this in the previous section when we talked about Amazon Nova. Now, the only thing that we have to add here is along with the prompt, we need to give the relevant chunks. That means we have to perform vector search in our database and get the relevant chunk. And those chunks need to be passed along with our prompt. And that is what we are doing here in this for loop. So this function takes our question along with the matched context or the relevant chunks. And what we are doing in this for loop is we are going over those relevant chunks and we are appending to our message content. That's all. Because at the end of the day, when we send the final prompt to the model, we need to have all the chunks added into the prompt. And that is what we are doing by looping over these matched items. And once we have that, we can call the same Bedrock client. So in this case, we are using client.invoke, not the model invoke. And the reason is we are not using Boto3 in this case. We are using the chat Bedrock client. So this chat Bedrock client is the client that comes with LangChain. So if I just scroll up, you will see that I have imported chat Bedrock from LangChain AWS. So we could have easily used the same Boto3, but I just wanted to show you how you can use LangChain to interact AWS models, all the models that are available under Amazon Bedrock, which internally uses Boto3. But in this case, I just thought to show it to you how we can use LangChain to invoke any model. So we have the model ID, and we just have to create a chat Bedrock a client object, similar to how we have created Boto3 Bedrock a runtime client object. So here we are just creating this. And once that is done, we can just call the invoke function and parse our data, right? And this request contains the system message, our message, and the inference parameter. And this system list, or sorry, this message list consists of our prompt and the relevant chunks. So let me execute this. And now we can test our RAG pipeline. Let's say we have this query. Which optimizer was used when training the models? And we know the answer of this question is present in our dataset, which in this case is the PDF document. So before we perform a semantic search for this query on our vector database, we need to first generate the embedding of this query using the same embedding model which we have used to generate embeddings of our dataset. So that's why we are using the same function which we have used earlier to create the embeddings of our dataset. And once we get the embeddings of the query, we can send this embeddings of the query to our vector database and perform a semantic search. Not only that, we can also mention how many relevant chunks we need from the semantic search, which in this case we have mentioned as 5. That means we want the top 5 relevant chunk with respect to this query from our vector database. So let me execute this cell and try to get the 5 top relevant chunks with respect to this query. And if we now see the result, we can see that these are the 5 chunks. These are the index number of the chunks, that chunk number 64, chunk number 78, 54, 60, and 14. These are the most similar or the closest relevant chunk with respect to this query that we have within our vector database. So now that we have the relevant chunks along with our query, we can send both of them to invoke our Nova model to get the final response. And that's what we are going to do here. We are taking the matched items from the result that we have seen, and then we are taking those matched item along with the query and calling this invoke Nova multimodal function, which we have seen a while back. So let me execute this cell and see what the model generates. And as you can see, the model has rightly predicted the answer, as the optimizer used when training the models was the Adam optimizer. So that's the power of multimodal RAG, wherein you can have your data of different modality, you can process it and store it in a vector database, and you can question your data set. So this is how you can leverage any foundational models to work with your proprietary data. Lastly, I have added few sample questions in case you would like to experiment a little bit more with this pipeline on this particular data set. You may like to execute these queries and see it yourself. But I would strongly recommend you to use some data set which is relevant to your business or your interest, and change the code, use different frameworks, different hyperparameters, and see how the response is changing. So that would give you a better understanding of different components in this pipeline. So that's all for this section. In the next and final section of this course, we are going to learn about agents and knowledge bases. Knowledge bases is one of the service that we have within Amazon Bedrock, which enables you to build end-to-end RAG pipeline. And we are going to learn about knowledge bases and agents by taking a real-world use case in the insurance industry. In this last section of the course, we are going to learn about Bedrock agents and Bedrock knowledge bases. We haven't talked about all these so far in this course, but what we will do is we will take a practical use case example. In this case, it is going to be an insurance claim lifecycle automation project, and we will see that how we can make any insurance claiming lifecycle workflow completely automated using agents and Bedrock knowledge bases. So before we dive into this particular use case, let's talk about Bedrock knowledge bases and how it is related to RAG and what are the benefits that you get with knowledge bases. So we have already talked about a RAG in the previous section. So to recall, we understood that in RAG, the first part is data ingestion, wherein you have your data, you have to process your data, you need to use an embedding model to create the embeddings of your data and store it in some vector database. And once you have that, you can use your application to send the query. And that query need to be embedded first, and then it can perform a semantic search on your vector database to get the context or the relevant chunks based on your query. And once you have that context, you can send your query along with the relevant chunk to the large language model to get the final response. So this is the whole life cycle of RAG. And if you think about it, the bottom part of this architecture is nothing but the data ingestion workflow, because this is something that you have to do every time you have a new data. You have to first embed them and store it in a vector database. And the top part is basically the text generation workflow, wherein you actually ask the question, and that question goes through a semantic search process to get the context, and then you take that question along with the context, which you get from your proprietary data, and finally you get the response. Now, in this whole scenario, there are a lot of challenges. One of the challenge is you have lots and lots of data. And in that case, managing all those data sources and its vector embeddings is very cumbersome. And one of the challenges that we often see at different customer places is wherever the data changes very frequently, you need to have the team to make sure that the incremental data is added to the vector database on time, so that when you query about a recent event, the relevant chunk should come from that recent data. So you need to have an entire life cycle of data management in terms of data ingestion. And again, you need to have a mature team who can perform all the embeddings, who can take the decision of which embedding model to use, what type of chunking strategy to implement, and so on and so forth. So there are a lot of challenges that we have in traditional RAG if you want to build it of your own. So this is where Bedrock knowledge bases comes into picture, which is a fully managed service within Amazon Bedrock, which can help you to do end-to-end RAG workflow management. And it is powered by different foundational models. So you can select any foundational model of your choice to embed the data and to finally generate the response. And everything under the hood, Bedrock knowledge bases will take care on your behalf. So if you think about the architecture that we just talked about, Amazon Bedrock knowledge bases will completely take over your data ingestion pipeline. So you don't have to worry about data ingestion, vectorizing the data, selecting the vector embeddings, making changes in your data pipeline. Everything will be taken care by Bedrock knowledge bases. So basically, it does all the heavy lifting on your behalf. And now that you have everything under knowledge base, what you can do is you can simply use the retrieval API by sending your prompt to get the relevant chunks. So everything has been abstracted under the hood by knowledge bases. So you don't have to create the embedding of your query. You don't have to perform the semantic search of your own in your vector database. Everything has been abstracted by knowledge base. Similarly, we have another API called retrieve and generate, which will not only retrieve the chunks, but it will also take those relevant chunks along with your query and send it to the generation model, and it will give you the final response. So if you compare with the previous architecture and this one, you will realize that once you have your knowledge base, your application workflow becomes very, very straightforward and simple. So all you have to do is call this retrieve and generate API. And we are going to see how you can create a knowledge base. So let me open the Bedrock console and show it to you how you can easily create a knowledge base with your own data. So once you log in and you come to the landing page of knowledge bases, this is what you will see. And to create a knowledge base, all you have to do is simply click here on create and select this option, knowledge bases with vector store. I have already created a couple of knowledge bases which we are going to use for our insurance use case. Specifically, this is the knowledge base that contains all the information about an insurance company. We mimic this. This is not real data, but I'll show you which are the data that we have used to create this knowledge base later on. But to create a knowledge base, all you have to do is click on knowledge base with vector store. There are a couple of other options that you have. You can create a knowledge base with Kendra. You can create a knowledge base with structured data store as well. So this is something that we have introduced during reInvent 2024, where you can select a Redshift cluster as a data store. So If you are not aware of Redshift, Redshift is one of the fully managed service within AWS for data warehouse needs. So for this demo, we are going to create a knowledge base with vector store. So once I click on this, I get an option to give a name for my knowledge base. So let me give a name. So let's say KB demo. So this is just the name of the knowledge base. You can put any meaningful name depending on your use case. You can put some description. You need to provide an IAM role so that the knowledge base can access your data store. In case you have not created any service role, then you can select this option, create and use a new service role, and Bedrock will create a service role on your behalf. And if you have an service role already created, you can select this option. So let's go ahead and select this create a new service role. And this is where you can select the data source. So the data source that you can have could be an Amazon S3 bucket. It could be even a web URL, and it will just crawl through your website and use that data to create the embeddings and store the embeddings for your retrieval. And you can even give any third-party data source like Confluence, Salesforce, SharePoint, and so on. Okay, so for this, we are going to select S3 and simply click on next. So there are a few other options that you may like to set up. Like this is a very important configuration where you can enable logging so that you know what is happening in your knowledge base. So when you click on add, and you can always do this at later point in time, but I would highly recommend that you enable log deliveries so that you can see what is happening in the CloudWatch and you have those logs for future analysis on S3. Okay, so this is just an optional thing that you should enable. So once you click next, this is where you need to provide the actual data source. So since we have selected S3 in the previous visit, we have given the option to select the S3 bucket. So you can give some meaningful name to your data source. So for us, it is going to be the insurance data. So I can say insurance data, and we can select the S3 bucket. So let's select the S3 bucket that we have. And these are all the insurance related documents that we want our knowledge base to have. So if you see, it has some claim documentation for different customers. So these are the customer ID, and these are the claim documents for different customers. There are some documents like driver insurance file, which consists of all the information that are needed for any customer who takes a new insurance. So when you take an insurance, the insurance company asks you specific details about your driving license, about your vehicle. So all those requirements are mentioned in this document. So let's select this whole folder. And inside this, we have seen there are a lot of files. So knowledge base will extract all the files and create embeddings of its own. So we don't have to do anything. So let's select this S3 bucket. In your use case, you can put the right S3 bucket where you have all your data. And once that is done, you can use a couple of different strategies to parse your document. So you can always go with the Bedrock default parser, but you can even go further and use a foundational model which can help you to parse your document. Now, this is an advanced topic. We are not going to dive deep into this, but at its core, what you are letting the knowledge base do is you are telling that go through my data and use one of the model, Claude 3.5 and Claude 3, and let the model decide what should be the right way to parse my document to create the embeddings. And this is very useful when your data is very complex, which contains images, text, tables, and so on. So if you remember in the previous section, we took an example of PDF file which contains images, text, and tables. And we actually segregated all those different entities of our own. So you may like to try a similar data set and use one of the model to parse your data so that it can perform the chunking and embedding in the right and the most efficient way. So this is something that you may like to explore in terms of parsing strategy. Then we have a chunking strategy. So by default, you can chunk the data based on the token sizes that we have. So when you use default chunking, what knowledge base does is it actually splits the data into a chunk approximately with 300 tokens. And this chunking process honors sentence boundary and ensures that complete sentence are preserved within each chunk. So this is just one option, but there are many different options that we have. For example, fixed chunking allows you to customize the size of text chunk by specifying the number of tokens per chunk and the amount of overlap between a consecutive chunk. And if you remember in the previous section, we used fixed chunking when we chunked our text data using LangChain. So here you don't have to write any code, you don't have to use any framework like LangChain. Everything will be taken care by knowledge bases. And there is another technique called hierarchical chunking, which involves chunking by organizing it in a nested structure like child and a parent. So in this approach, what we do is knowledge base will chunk your data in parent and child format. So let me show you how it works. Let's say you have a data and it will chunk the data under parent, which would be a bigger chunk. And then within that parent chunk, it will have child chunks. So in this case, let's say each parent chunk contains 5 child chunk. So the way that you should think about it is you have a bigger chunk, which is a parent chunk. And within that, you have a second level of chunking, which is called child chunks. And all these child chunks will belong to one parent chunk. And what is interesting here is while you do a semantic search, the semantic search happens on all these child chunks. And once it find out the relevant child chunk, let's say the most relevant chunk for a specific query is chunk number 12 and chunk number 13. What knowledge base will do is it will not send chunk number 12 and 13, but it will send the parent chunk. So in hierarchical chunking, we return parent chunk and the semantic search is performed on child chunks. So therefore, you might see lesser number of search result returned as one parent is sent at the end of the day in case it found 2 or 3 child chunk, but in the retrieval process, you will get just one parent chunk because all those child chunk are part of one single parent. Right? So this is very efficient in the sense that you are doing the semantic search on a smaller chunk, but when you are sending the chunk for downstream processing or for generation, you are sending a bigger chunk. So the bigger chunk will always give a broader context for the LLM to generate the final response. Now, this is beneficial, but this also have some side effect that the moment that you give a bigger chunk to LLM, it might contain some noise. So you need to play around with this and find out which type of chunking or which strategy of chunking works best for you. Okay, so that is about hierarchical chunking. And then you have semantic chunking. So semantic chunking is a natural language processing technique that divides the text into meaningful and complete chunk based on semantic similarity calculated by the embedding model. So if you have selected semantic chunk, you are given a few options like what should be the maximum buffer size, what is the maximum token size and the breakpoint. So for example, let's say your buffer size is 1. What that means is if you have three sentences and the buffer size is 1, then it will take 3 sentences. The current one, the previous one, and the next one. So let me just show you in Notepad. If the buffer size is 1, so in that case, it will take the current, the next, and the previous. Right? So this is what it will take. And if you have a buffer size of 2, then it will take the previous one, previous 2, and then current, the next one, and next 2. And similarly, with buffer 3, it will take 6 chunks. So that is how semantic chunking works. It tries to find the best chunk size based on the context. Okay, so that is also very much useful in few scenarios, and you may like to explore semantic chunking if that works best for you. So for now, we are going to use a default chunking, but you can select different types of chunking techniques as mentioned here. And of course, there is a technique called no chunking, which means there won't be any chunking and the knowledge base won't be doing any chunking. So it will be like one document, one chunk, as long as that fits the size or maximum size of our embeddings. Okay, so let me select default chunking. And before I go ahead, I'm going to share few of the blogs we have, and that will give you more intuition about chunking strategies. So this is one of the blog that I've written, which covers all these chunking techniques. And I've also mentioned the code, how you can parse different configuration for different chunking strategies, right? So this will give you an intuition how all of these work in a real world. And then there is one more blog which is written by one of my colleague, Shreyas Subramanian. And here you will learn about all these different chunking techniques. And also he added 5-6 seconds clip of different chunking techniques so that you can visually understand what these chunking techniques actually does under the hood. Okay, so I will attach all these blogs in the GitHub repo so that you can refer to them as you go along. Okay, so now that we have selected our data source and we also selected our chunking strategy, we can go ahead and select next. Okay, I have used foundational model, but I have not selected any model. That's why it is giving us this error. So let's go ahead without any foundational model as parser and click on next. And here we have been asked to select the embedding model. So we need to embed our data or to build our vector database. So that's why we have to select one of the embedding model. So let's go ahead and select Titan Text Embedding version 2. And here we have an option to select any vector database of our choice. By default, it is going to create an OpenSearch serverless instance, but we can always select vector database of our choice, like Aurora, MongoDB, Pinecone, Redis, and so on. For this demo, we are going to create a new vector store, which is going to be an OpenSearch serverless instance. Once that is done, I can click on next. And here, all you have to do is you need to make sure that all these informations are correct. And you can simply click on create knowledge base. So under the hood, what is happening at this point in time is it is creating all the resources that are needed to make your knowledge base ready. So this might take a couple of minutes. So as you can see, it has already created the OpenSearch vector database and it is ready. And if I close this message, you will see that it has now started creating the knowledge base. So what we will do is once this process is over, we will sync the data. So that is the second step that you need to do. So as you can see, it is all done. And let me just hide this testing console. It is saying that sync your data source to index your content for search, right? So if you now ask any question, you will not get any response because the data is not yet synced. So the moment your knowledge base is ready, what you need to do is you need to select the data source and click on sync. And when you do that, under the hood, knowledge base will go through all your data, and based on the chunking strategy that you have selected, it will chunk your data and it will embed your data based on the embedding model that you have selected, and it will store the data into the vector database. So as you can see, the knowledge base is now ready. The data is also being synced, and now we are ready to test our knowledge base. And to perform a test, we can click on test here, and here you get an option called generate response. So if you remember in the presentation, we have seen that knowledge base provides two types of API. One is retrieval and another is retrieval and generate. So when you disable this, what you will get is just relevant chunks. You will not get the final response. But when you select this option of generate response, under the hood, it is going to call retrieve and generate API call. And that's why you have to select a model, because now you are telling knowledge base not only to just retrieve the relevant chunk, but also send that chunk along with the query to the model to get the final response. So let's select one of the model and ask some question. Let's see what question that we can ask. I guess I have drafted few questions, so let me just find that out. Yeah, so let's ask this question. What should be the driver do after an accident? So this information is there in the documents which we have uploaded on the S3 bucket. So there is a document where we explain about what are the requirements that driver should do after an accident and while placing a claim request, right? So let's ask this question to the knowledge base and see what answer we get. So let me paste this question and click on run. And as you can see, it is able to generate the response based on the data that we have. And not only that, it is also giving some citation. So this is giving us from which chunk or which part of the document it is able to generate this response. And if I disable this option and if I now ask the same question, at this point, it is not giving us the response, but it is actually giving us the exact chunk which are semantically closest to our query, right? So these are the two APIs that you can have with knowledge bases. One is the retrieval API, and the other one is retrieve and generate API. So this is how you can create a knowledge base in a couple of minutes by selecting the embedding model of your choice, the vector database of your choice, and providing the data source where you have your data. In this case, it was S3, but we have seen that it could be a SharePoint or a website or a Confluence page and so on. So that's the beauty of knowledge base, where it can do all the heavy lifting on your behalf and create an end-to-end RAG based system so that you can focus on your business logics and you don't have to worry about LLMs, vector embeddings, and managing the data sources. In fact, we talked about one of the challenge in RAG called incremental data ingestion. So this is now very much simplified. So as you can see here, if I have a new data, I can simply select the data source and click on sync. So we are doing it through UI, but this can be done through the code as well. You just have to send sync call so that it can synchronize with your data source, and your vector database always contain the latest data, right? So this has eliminated few of the limitations that we have traditional RAG if you do it yourself. And you can also add a different data source at any point in time. It's not like you have to stick with the same data source that you have added at the time of creation of the knowledge base. So you can always add different data sources at different point in time as your business grows, as your data grows. Okay, so now that we have our knowledge base, we will discuss about function calling and agents, because that is something that we are going to use in our insurance lifecycle automation management system that we are going to build with agents. Thank you so much. I'll see you in the next section. So before we talk about agents, we need to talk about function calling. So function calling is a capability that allows any foundational model or large language model to interact with external tools or APIs or databases. So the way that you should think about function calling is something like this. Imagine that you need to know what is the present time, and you are asking this question to an LLM. LLM won't be able to give you the right answer because it doesn't have any live data, or it doesn't know the present time. So imagine that you have a function that is a clock function, and you could send that function details and then ask a question. At that time, the LLM might say that, okay, this question seems like a question about time, and you have also provided me that there is a function called clock. So please call this function. You should be able to get the answer. So that is what function calling is all about. So it doesn't actually execute the function, but it is just recommended by the LLM based on your query that it should run this function. So this is a typical function that we have in any program. You write different functions and then you call those functions from your application code. So let's say you have a function 1, which is a clock function. There is a function 2, which for multiplication, and so on and so forth. In this case, in a traditional regular function, you have to decide which function to call, and then you have to call that function. And of course, you have to write all these functions of your own. Now, this is where function calling comes in, where you have your application code and you also have your function. But what you do is you call the LLM with the function descriptions and your prompt, and LLM will tell you which is the right function to call. Again, it is not going to call that function, but it will tell you that call this function number 1, because this question or the prompt that you have provided can be answered by function number 1. And then you have to write the logic in your code to actually call that function. Okay, so with respect to traditional regular function, here we were able to automate certain things. Like in this case, I don't have to think about which function to call. So that help I'm getting from LLM. But at the end of the day, I have to call that function to make it work. So this is a good amount of automation, but it would be great if we have a system where the LLM would not only select the right function, but it will also execute that function. And that is where agents come in. So agents are nothing but an advanced AI system. You can just intuitively think of it like that, which automatically figures out how to best answer your question. So if we compare function calling with agents, this is what function calling that we have seen a while back. And what makes agent different is this. Now, when you have a question, you will send that question to the agent. And agent will internally ask the question to the LLM. So agents are nothing but it contains an LLM, and it also have a lot of tools attached to that. And we are going to see how we can leverage Bedrock agent to implement all of this. So at this point in time, the LLM within the agent will pick the right function, and it will also execute that function. So agent will decide which function to select and which function to execute. So now it's completely automated. And now you can think of various scenarios where you can build a fully automated pipeline with agents, because now you are having the capability of reasoning. So given a problem, let's say, tell me the best route to go to New York from Boston during December. It's a very complex question. So imagine that you are asking this to an agent, and agent has a lot of functions and tools added while the system was built. So first thing that it has to do is it has to know the distance between Boston and New York. So there might be a function which can find the distance between two locations. And once that is done, the agent might take the next step to find out the best route to go from Boston to New York. It could be via flight, it could be via drive, and so on and so forth. So, with agents, you can make your software much more agile. All you have to do is you need to select an LLM and give the right tools and functions which the agent can use. Okay, so now that we understood agents, what we are going to do is we are going to work with agents with knowledge bases. So the way to think about it is like this. So we already have knowledge bases where we can ask questions and get the response. And now that we learned about agents, what if we give knowledge base as one of the tool to the agent? In that case, the agent can go and call the retrieve API as and when the agent needs. This is the advantage of using knowledge bases with agents. So let's say you have built an agent on Bedrock, and we are going to see that in the demo in a couple of minutes. But I just wanted to show you how the workflow would logically look like. So you have a question, you ask that question to agent, and now the agent will split your question into multiple tasks. And this intelligence it will get from an LLM. So this is where the chain of thoughts and reasoning comes into picture. So you ask something, agent will break that task into subtask. And each of the subtasks will be executed in sequence or in parallel depending on the subtasks. So let's say the first couple of tasks, it need to send to some action group to get that done. So we will see what are action groups, but action groups at its core are basically the actual functions or actual business logic which can solve a particular task. So in our previous example, when we created some function to add two numbers, some function to calculate the distance between two locations, you can think of them as action groups. Similarly, with agents, you can also attach knowledge base. So in case any of the tasks needs to be searched in a knowledge base, you can actually provide the knowledge base and agent will select that knowledge base to get the relevant chunks or the response. So you are not doing anything of your own. Everything is taken care by the agent. So you just ask a question and it breaks down that question into multiple tasks, and those multiple tasks or subtasks gets the right response from its respective action group or knowledge bases. And it is not mandatory to have action groups and knowledge bases both. These are the options that you have when you create an agent. You can have action groups or knowledge bases or both of them. And once you get all the response for all the tasks, you can get that response back, and that response is sent to the agent. Now, as an end user, you have not yet received the final response. At this point in time, the agent may decide to send that response to the user as is, or it may decide to refine the response by sending it back to the model, and that model will give us the final response. So if you think about it, everything here, starting from prompt, the conversation, the actions, the knowledge bases, instructions, a task, everything is taken care by the Bedrock agent. And it has fully automated the whole pipeline. Okay, so that is what makes agent so powerful in today's time. If we go back to our problem of insurance lifecycle management, we have different types of data. We have seen few of the data while creating the knowledge bases, but there are different types of data that we have dumped into the knowledge bases. And now what we are going to do is we are going to use knowledge bases with agents and see how we can leverage the power of agents to, to make our system more sophisticated. Now that we learned about what agents does, let's forget about all of this and let's see what kind of question we can expect the agents to answer on our behalf. So now we can ask a question like create a new claim, and the agent will go ahead and create a new claim based on the action groups that we have created. We can have some question like this: what factors determine my car insurance premium? So this question can be answered by the agent if we have a knowledge base attached to that, because all these information is kept in some document based on my insurance company's policy. So what the agent can do is it could go to the knowledge base, send this question, find out the relevant chunk, and process that with the LLM and send the response back to the user, right? So we were able to ask a lot of questions without looking into our backend data and without selecting the right function which can help us to get these questions answered. So if we look into this workflow and if we ignore all of this, the underlying data flow, we will end up into action groups and knowledge base. So let's focus on this because we have not talked about action groups and knowledge bases. So let's see how action groups actually works. So when you ask a question, the Bedrock agent will trigger an action group. So there are different action groups which you can add to your agents. And each of these action groups, the way that you should think about it is the business logic, as I explained earlier, or the functions that you would like to have for your business. For example, in this particular insurance use case, we have couple of tasks like creating a claim. So I know that there will be instances when the customers will request to create a claim. So in that case, the agent should have the capability to create a claim. So that's why we created an action group for creating claim. Similarly, there could be another action which we might get from the end user, like gather evidences. So imagine that I have to ask question to all of our customer to provide all the relevant documents to process a claim. So that means I have to provide a URL where they can upload all the documents for a certain claim. So all of that logic, like where to upload, what are the documents to upload, all this logic I can incorporate in an action group, and agents can call that action group if needed. Similarly, I have also have a requirement to send reminders to different customers for renewals or let's say premium. So in that case, I may have a action group which will go over all the customer IDs and send a reminder email automatically, right? So all of these business logics can be included in different action group. For example, let's say we have an action group for create claim. So when a user sends a request, create a claim, that action group create claim will trigger a Lambda function. And that Lambda function will contain all that business logic that we talked about. And after creating a claim, it has to store in some database like DynamoDB. So everything here will be taken care by the agents itself. The only thing that we need to do is we need to provide all these resources, all these action groups and knowledge bases to the agent. Similarly, once we create all this, once the agent executes all of this, it can send the feedback or send the response back to the agent. Likewise, there might be situations when you have to ask some question where the answer lies in the knowledge base. And then the knowledge base will be triggered and the agent will get the response from the knowledge base, and it will finally send the response either to the user directly or to the LLM, and then the final response from the LLM will be sent back to the end user. Okay, so that's the power of using agents with knowledge base. So let me show you how you can create an agent and how that action groups and knowledge bases looks like within an agent. So let me go back to the AWS console, and we can click on agents on the left hand side. And if you see here, I have already created an agent. And the way to create an agent is again very, very simple. You just have to click here and create an agent. Since I already have an agent, let me click on this and show you what are the things that you see within an agent. So you have this agent name, some description about this agent. So since this is the agent for insurance claim management, the description is you are an insurance agent that has the access to domain specific insurance knowledge, right? So that is the agent description. And if I click on this edit in agent builder, you will see different action groups and knowledge bases. So here, when you create an action group, which I have already created, so let me just show you how we can create. So when you click on add, you will be given an option to enter the name of an action group, and then you can optionally give some description. And then this is where your business logic comes in. So you need to create a Lambda function, or you can let Bedrock to create a Lambda function for you, and then you can edit that. But you can create a Lambda function which contains the business logic and select the Lambda function from here. And here you will be able to see all the Lambda functions that you have within that particular region and in your account. And you can select different Lambda functions for different action groups. So in this case, if you see, I have a Lambda function to create claim. I have a Lambda function to gather evidences. I have a Lambda function which will send a reminder to all the customers. So in that case, this Lambda function will internally talk to the DynamoDB table to get the information about all the customers and send an email or an SMS to all the customers. So this is how you can create action groups. Similarly, you can also have knowledge bases. So let me just cancel this, and you will see that you can also select a knowledge base. So since I have one knowledge base already created, I have attached that knowledge bases to this agent. And of course, agent needs not only a knowledge base and action groups. The most important thing for agent to work is the large language model. So you need to have a large language model attached to the agent. And that's what makes the agent as AI powered agent. So you can always select different models. So let's select Nova Pro. And this is the model that the agent is going to use when I select it here. And you can always change this model and try out your prompt and see which one works the best for you. So what I have done is I have created a Streamlit application, which I'm going to run now so that we don't have to ask a question on the console. And in the GitHub repository, which we have for this course, if you come to this folder number 4, so this is the last section of the course, you will find a tutorial on how to set up the system. So there is a CloudFormation template attached to this repo, which will create a DynamoDB table, which will create the Lambda functions and all of that. So you don't have to worry about setting this up. And once you are done with this, what you have to do is you have to go to agents, and within that there is a folder called Streamlit, and there is a script called setup Streamlit environment. So this will create a virtual environment in your system, and then you can simply run this Bedrock Streamlit.py file. So let me go to the CLI and run this. So this is the Streamlit application, and this is present under the Streamlit folder. So if I run this, it would open up in a browser, and this would be the landing page. And here we have a couple of options. So you can ask any specific question to the knowledge base directly. So in that case, you are just asking the question to the knowledge base, but you can also select agent and select the agent name. Since we have only one agent, that's why it is showing just one. But if you have multiple agents configured in your account, it will have all the agents here. And then you can select any model for that agent. So let's select Nova Pro. So this is exactly same as selecting a model in the AWS console, which we have seen a while back. And then we can ask questions here. So let's try this out. So let me copy some question. So let's say we want to create a claim. Now, when we call this, we know that this question cannot be answered by looking into the knowledge base. But to get this job done, this is not actually a question and answer, it's actually a task. So when we ask this question to the agent should be able to detect that this is a question about creating a claim, and I have a action group which can help me to create that claim. So it will go and call that Lambda function, and that Lambda function will create a claim, and it will update the DynamoDB table, and it will send a response back to the end user. So let's see how this can help us to create a claim automatically. So let me copy this question and paste it here. But before I do that, it would be great to see the number of items that we have in the DynamoDB table so that we can verify that it is actually creating a claim. So this is the DynamoDB console. And if I come to tables and select the table that we have for this, which is a life insurance demo existing claim, and if we get the live item count and perform the scan. Now, performing scan is not recommended like this, but since I know the size of the table is very small, it is okay. So we have 29 items at this point in time. That means there are 29 customer information present in this database. So if I go ahead and ask this question, create claim, and hit enter, I expect that the agent should be able to call the action group, and the action group will trigger the Lambda function, and the Lambda function will create the claim, and it will store the details in the DynamoDB table. As you can see here, it says that the claim has been created with a claim ID of this. Right? So this is the claim ID that it randomly generated. So this logic is mentioned in the Lambda function. So now if we go back to DynamoDB table, and if we scan it here again, we expect that the item count should increase by 1. So let's try and see. So as you can see, the item count is now 30. Right? So let's try to ask some more questions. So let's say we have already created a claim. Now the next natural thing to do is we need to provide a system, or we need to provide a URL to the customer so that they can upload the evidences for this claim. So let's paste the new claim ID which we just got, and copy this question and ask it in our Streamlit application. So let me paste this question and hit enter. So now what the agent is supposed to do is it is supposed to find out that this question can be answered using an action group called gather evidences, and it should run that Lambda function. And here, if you see, it is saying that to upload all the documents in the below URL for this particular claim. Now, this is a fake URL which I have just mentioned in the Lambda function, but in real world, this would be the actual uploading website wherever you would like your customer to upload the evidences, right? So if you think about it, agent is doing everything logically. So it's not that I am dictating anything. All I have done is I have created an agent and given that agent all the resources in the form of action groups and knowledge bases so that it can pick the right one based on the agent's understanding, right? So let's now ask some question where the question can be answered from the knowledge base. So let's pick one question. So let's ask this question. What is recommended for the accident report and images? Now, for this particular question, we don't expect the agent to call any action group. So this question can be answered from the knowledge base. So let's go ahead and hit enter. And this time it should go and talk to the knowledge base, not the action groups. So let's wait for a couple of seconds. So as you can see, it says that to submit an automobile accident claim, you should provide the following documents: the vehicle registration, driver's license, accident report, and accident images. Okay, so now you might appreciate the fact that how powerful agents are. If we provide the right set of tools to the agent, it can do wonderful things. And this is how you can fully automate your pipeline and make your application very, very powerful. And you can actually make your end user experience better, right? So that's all for this particular demo. In case you would like to run this in your account, as I mentioned earlier, you can come to this knowledge base agents folder that we have within this GitHub repo. And the first thing that you should do is click on a deployment guide. And once you click on this deployment guide, it will tell you how to implement this. Okay, so it will tell you which are the scripts that you need to run to set up the environment. And we have a CloudFormation template. So if I go to TNF folder and you see this, there is a YAML file which will get executed once you run the script. Okay, and this will also give you some idea about the cost because there are a lot of components here. For example, there is a Lambda function, there is a DynamoDB table, and there is a knowledge base, and so on and so forth. So you need to know how much cost this might cost when you actually implement this, but you can always give it a shot and see how things work. Okay, so that's about this course on multimodality, multimodal RAG, embeddings, agents, and knowledge bases. We have started with embeddings and then we moved to multimodal embeddings and then to multimodal LLMs. And finally, we ended up with agents and knowledge bases. So I hope that you learned a bit about all these. And this is not the end. This is just the beginning. And I'm very sure that all of this might be a little overwhelming. And in general, this entire space is a little overwhelming, at least to me, because every day something new is coming up and it is very difficult to keep up with the pace. But what I always found very helpful is if we don't focus on a particular tool or service and focus on the underlying concepts and foundations, it becomes very easy for me to ramp up on a certain technology. So rather than focusing on LangChain or Llama Index, it is better to focus on how prompt engineering works, how different techniques work to chunk a data, how embedding works, how a multimodal model generates an image, or how a multimodal model are actually trained. So these things will help us to understand how a fully managed service work, and in that way you will gain more confidence when you build something, and also you can explain to your customers in a much better and confident way. Okay, so with that, I'm going to end this course, and thank you so much once again to be with me throughout this course. And I really appreciate that you reached to this point. And I would request you to stay connected with me. And I'm going to share my LinkedIn. Maybe I'll add that on this GitHub page, but I will also share my LinkedIn ID towards the end. And I hope that we will be in touch. And in case you face any difficulty while going through these examples and these notebooks, feel free to reach out to me over LinkedIn. But if you feel that something can be added in this GitHub repo and you would like to contribute to that, feel free to create a pull request or just ping me directly on a LinkedIn or send an email. Now, before we wrap up, one thing which I have not added in this GitHub repo as of now, but I think by the time you will watch this, you should be able to see that. So I will add a resource section where I will add all the resources that we talked about, like different blog posts, then different books that I have shown you. And also there are some very good advanced courses around LLMs, which I recently have gone through and still going through. You may like to check them out. And I wish you all the very best in this journey of AI engineering. And I hope you will build something meaningful and share it with others, and hopefully with me as well. And I'm looking forward to see what you build by acquiring all this knowledge. Thank you so much once again for being with me throughout this course.